Hi, Devu. Good morning.
Yes, hi, JRK. Can you hear me?
So
I
I
think you
can't.
can hear,
I
right?
can't hear him. Is it?
You can hear me. Okay, wonderful. Okay, so we are all set.
There is a sound here. Is there a mouse external? No.
No external mouse.
Oh, he is blocked out. Hi, can you hear me?
I can hear you.
Oh, good, good, good. Yeah, I can
Oh,
hear
you
you.
can. Okay,
Sure.
wonderful.
Looks
Good.
like we woke you up.
No, no. We had a PMRF interview, which and the discussions on it went on pretty late last night.
Are baap re.
And had some 20 applicants, and then had to start
Yeah,
discussing about it.
sure.
Good to see you.
Yeah, same here. So we'll just wait for the other people to come in.
Sure, sure.
Chandrabas won't be there, but the
Yeah,
others,
yeah, he's down with COVID. I saw that.
yeah. It's unfortunate.
Yeah.
Sure.
So now we are waiting for Dr. S.R. Misra.
Yeah.
Just a few more minutes. We will try, and we are trying to connect him.
Okay.
So Ravi, are you joining from home?
No, I'm in BRC.
Okay, okay, good.
Yeah, it's really tragedy that we are all not here.
No,
Remote. I mean, this has just
it has
gone on
been
too long now.
it has been a while. I have actually traveled.
It's really sad. So just 1 minute. I'll just check some things and come
Sure,
back.
sure, sure. Right. Good. I'm happy that everything is working. Thank you.
Uh, Dr. Goswami, can you hear us? Are we
Yes, I
audible?
can. Yeah, yes. Very
Okay,
nicely.
sir. Okay, sir. Your voice is also clear and audible. Thank you, sir.
Wonderful. Thank you.
Dr. Rao, can you hear us? Uh, Dr. Tirumala Rao, can you hear us?
अरे प्रवीण अरे ये मिश्रा जी से कांटेक्ट करने की कोशिश करते हो थीसिस में अभी जज है ना वो
Hello, I can
वो
hear.
फोन उठा नहीं रहे या तो फोन बिजी आ रहा है
Hello?
Hello,
हाँ
hello.
हाँ डॉक्टर राव कैन यू हियर अस?
अच्छा उनको मैसेज कर दिया
Hello.
हाँ हेलो हेलो
I'm BT
लिटिल
Rao
लाउडर.
speaking. Yeah. I'm BT Rao speaking. Am I audible?
Yes, yes sir.
Okay. Thank you. Okay.
Okay.
Dr. Mishra hasn't joined.
Yeah, he hasn't. Okay,
Start.
we start off. Sure. Yeah. So, great. Who is the third judge? Debu is here. Tirumal Rao is also. Yeah. Sure. Hi, Tirumala and Debu. We're going to start now. Hello. Can you hear me?
Okay, sir, shall we start?
Can you just check that they're there?
तो इधर देखो मिश्रा जी इधर अटेंडिंग में हो सकते हैं क्या आ जाए
नहीं हम वेट नहीं करेंगे
नहीं उनके लिए वेट नहीं करेंगे
लेट अस स्टार्ट 9 बजने हैं
कॉल नहीं लगा ना तो देखते हैं
ओके सो फर्स्ट किसको बुलाना है वो
तुम्हारे पास ईयरफोन नहीं है? मैं दूं? मेरा वाला है।
हाँ तो आप
Sure.
ओके इट्स 93 स्टार्ट
I'm there.
Sir, shall we start?
Yeah, we should start. I just want to tell the judges to make their markings. I think at the moment there's just two of us, Tirumal Rao and Debu.
Hello. Hello.
Yeah.
Yes.
I am Tirumal Rao. I am there. You
Yeah,
can
yeah,
start
you're
the session.
I can start. We can start the session.
Okay. So,
Please
sir,
make your markings and then we'll discuss at the end of the presentations. Okay, we can start as soon as the first.
okay. So, good morning, everybody, and now we will start our PhD thesis presentations, and I request all the presenters to be online during this whole time up to 11:30, and it's a kind request to all the presenters as well as to the judges to maintain the time, and the time schedule would be like you will be given 12 minutes to 12 minutes, total complete 15 minutes will be given. So first bell will be rang after 12 minutes and another final bell will rang on 15 minutes, completion of 15 minutes. So after which the judges will take over. So
And the
let's
final
start.
bill will be really hard in the sense that there won't be any people should not talk after 15 minutes.
Yes sir, we'll do that.
Okay.
So our first presenter is Dr. K.N. Krishnakant from University of Hyderabad. Dr. Krishnakant, can you hear us? Dr. Krishnakant, उनको please unmute yourself.
Can you hear me?
Yes, clear.
Okay, thank you. Yeah, I have to share my screen.
This ID, this one.
Hello.
kindly share your presentation
What are you doing? Told.
Can you see my screen?
Yes, please enlarge it. Yes, now it's clear.
Okay, I'm starting. I'm Krishnakant from University of Hyderabad. Recently graduated from University of Hyderabad. My thesis title is
Little louder, please.
My thesis title is Ultrafast Molecular Dynamics and Third Order Nonlinear Optical Studies of Novel Organic and Inorganic and Energetic Materials. My supervisor, Professor Swami Gopal Rao. So outline of the presentation, I'll give introduction and my experimental details and the results and discussion and dynamics of energetic materials, since our center is mainly for energetic materials, and summary of my thesis. The introduction is we are working on the third order non-linear optical materials, where as you increase your intensity, you expect to have higher order contribution to your polarization term. So we are interested in the Chi3 third order process. The Chi3 is a complex quantity. You have imaginary part and it's a real part. Imaginary part is correspond to your beta, that is a 2-photon absorption. So it is having different applications like ranging from dynamic therapy and 2-photon excitation and optical limiting studies. And in case of N2, we have optical switching. The switching performance mainly decided by chi3 value and its lifetime. The shorter the lifetime, you have the faster the serial processing of the switch. So we have used three different experiments to quantify the chi3 and its response. So for the first one is the G-scan, where you get its magnitude and magnitude and sign of the nonlinear parameters, where you scan your sample. This is the experimental layout, where you scan your sample along the focal perpendicularly to the laser beam focus. At the maximum intensity, if you have the maximum transmission, you expect to have saturable absorption behavior, and if it is minimum, you have a reverse saturable absorption. From the closed aperture regime, where you place an aperture in front of the detector, and you expect you will get a nonlinear refractive index. This is corresponding to your real part. So you get both real and imaginary chi3, and with that you can calculate the total chi3. Yeah, so this is experiment for G-scan, where you get its sign and magnitude. This experimental setup, where we have 50-50 1 kHz 800 nanometer system, and we have OPA. So we scan the laser beam using a translation stage, and you collect the output using a photodiode. The motion is controlled by ESP motion controller, Newport. And we also set up a degenerate Fourier mixing. I'll quickly degenerate Fourier mixing, where you take the Libra output and OPA. So as the name suggests, degenerate Fourier mixing, all the beams have the same frequency. So the three beams were aligned is in a boxcar geometry, and as shown in the corner. So this is our degenerate Fourier mixing signal, fourth beam. The fourth beam collector is in lock-in amplifier, and we also get a response and a magnitude of chi3 here. The response is measured by delaying one of the arm using a translation stage and recording the signal in time domain. And we place an ND filter. We can place aperture to collect the signal using photodiode. And we use a transient absorption to study the excited state properties, how the dynamics are varying in our different samples. This is a commercial Helios transient absorption spectrometer. This is a pump beam and is collected using a second harmonic from a BBO crystal. And this is a probe beam, where we use a titanium sapphire plate, and we make a white light, and we use it for probing the molecular dynamics. As my thesis suggested, we used organic and inorganic molecules. In case of organic molecules with d pi d and d pi donor pi bond and acceptor pi bond donor, this kind of molecules will have a strong NLO activity, like several studies reported, of the order of 210 into gigamolar units. And this is right side shows the Jablonski diagram, which represents different transitions which mostly participate in this nonlinear absorption properties, where you have sigma is your cross section, where you have sigma S0 is greater, sigma S is saturable absorption. If the sigma S1 is greater than sigma ground state, and you have a reverse saturable absorption up to limiting properties. So I'll quickly go to my results. We have studied these NLO properties from Paparin's and Carol, two systems. This is a Paparin which I studied. This is a Paparin ring is with penazazone, and center is doped with H2 and zinc and copper. This is a steady state measurements, absorption and emission measurements. These are the structure parameters, and this is a NLO data, where this is a G-scan curves at 800 nanometer and Fourier mixing at 800 nanometer. Yeah, as you can see, the NLO parameters are quite strong in zinc porphyrin, which is quite strong from zinc. It's then you move to this excited state dynamics. From the excited state dynamics, you can clearly see the ZN have a strong excited state properties. From the G-scan and transient absorption, we can say that this is having strong excited properties from zinc, and strong heavy atom effect, which is mainly showing its higher magnitude of chi3. And this is the result from global analysis of transient absorption spectrum. This is we have done in Auditorium software where we use a 4-level model to fit the transient absorption spectra. So the each time decay were estimated from this Auditorium software. These are the parameters of the lifetimes. Then we have studied the similar experiments in a Carol system. This is two Carol molecules, which is the free base Carol, where the center have uh, nothing in your center, and you have phosphorus Carol and another Carol. These are steady state measurements, absorption and emission spectra. The transient absorption. From the transient absorption, we can see that phosphorus Carol have a strong exhausted properties, which have a higher lifetime, and as well as the this is a global analysis spectra from the transient absorption of two Carol systems. And this is the NLO parameters at 800 and 600 nanometer. From this spectra, we have a little quite strong two-photon absorption cross section from phosphorus Carol system. And degenerate foreign mixing shows it have a fast response from the phosphorus Carol of 105 femtosecond with the full width of maximum, and above linear plot shows that it is a Chi3 process from slope 3.1. This is summary. There are two Carol systems. Carol and Porphyrin have a strong two-photon absorption cross section of 10 to the power of 3 GM, arising mainly from the strong exhausted absorption. Yeah, from the DFW measurements, you can have large Chi3 values of 6.2, 6.9, 10 to the power minus 14 ESU in solution. All the measurements are performed in solution. Time result DFW we have confirms the fast response is mainly arising from its pure electronic contribution. So, and in case of analytic part, we have studied this NLO measurements from perovskite, two perovskite system, that's CSP-BR3 and CS4-BB-BR6. These are two TEM images and HR10 images and their ground state properties. In case of CS4-BB-BR6, it's have two configuration. One is fluorescent and another is non-fluorescent, where it doesn't show any fluorescence. This is a non-fluorescent and this is a fluorescent one. They are all G-scan parameters. G-scan parameters ranging from visible to NIR range, means 500 to 1500 nanometer broadband studies we have performed. These slopes confirm that it is 2-photon and 3-photon and 4-photon absorption. These are total NLO quantities, which is 2-photon absorption, 3-photon and 4-photon absorption, which is having higher values, which is mainly from its quantum confinement effect. And as we decrease the size of the nanoparticle, you expect to have a strong Chi3 from these materials from the previous studies. Yeah, the NCS demonstrates strong nonlinear absorption coefficient of 10 to the power minus 10 watt per 10 centimeter scale and 2-photon cross section of 10 to the power 4 order. It is observed that CSP BR is depicted is a structural dependent thickness and size dependent NRO properties. And in case of CSO BR6, it is even higher parameters considering its size and higher quantum confinement effects. And later we have set up a CARS experiment to study this IVR dynamics, intramolecular vibration redistribution dynamics of energetic materials. Since energetic materials tend to decompose quickly in order of picosecond to nanosecond time scale. So as in case of conventional spontaneous Raman, it's a linear and incoherent spectroscopy and a very weak scattering. 1 in billionth of 6 photon will be scattered statistically, and in case of fluorescence background, it is very difficult to separate Raman signal. So this is the below picture shows the Raman process and the typical Raman spectrum. And the possible solution for this is going for a surface enhanced Raman or nonlinear spectroscopy such as CARS and resonance Raman like that. And coherent anti-Stokes Raman spectroscopy works. We use two laser pulses. When the Stokes difference between these two laser frequency we matches to any vibrational mode, that particular vibrational mode will be resonantly excited. And we use the third laser pulse to probe the chain dynamics of the particular Magma vibration. This is the energy equation, and this is energy level diagram for spontaneous Raman and cars, where you simultaneously use pump and Stokes, and this particular Raman mode will be exited and use the third probe beam and to see the car signal. Significant signal enhancement or Raman scattering will be observed. Anti-Stokes field is fluorescence free, and we have this is a drawback. It's a non-resonant background and very complicated setup. And these are intensity of anti-Stokes signal equation. The delta K is a phase mismatch, so we use a boxcar phase matching to overcome this issue. This is our setup which we built in our lab. We have used same laser setup, 50 femtosecond pulse and a OPA. We use OPA to tune the Stokes beam, and we collect the output using a spectrometer, and
I
we
think
move
you'll
the
have to wind up soon now.
yeah, this
Session
is
manager, are you monitoring the time?
Yes, sir, we are monitoring. It is about to be 12 minutes.
Yeah, okay.
We will put a bell on 12 minutes and a final bell on 15 minutes.
okay. So this is our final output signal, and we have taken the capture the signal. This is the cars beam, and this is the through three input beams. So there's a two molecular system which we have studied. These are the tetrazoles, amino substituted tetrazole and nitro substituted tetrazole. The below shows the pulse timing. The pump and Stokes pulse arrive at the same time, and the later you observe the propulse. Here's the DFT calculation, experiment and Raman spectrum. So these are the time result cars measurements, and this is the time result car spectra and the corresponding Fourier transform that we observe quantum bits. So we mentioned this. So this is the car spectrum and pump and Stokes pulse, and this is the power dependent car signal which confirms it's arising from Chi3. No higher effects are present. So from the quantum bits and the time result, from the quantum bits, we observed that 992 and 1466 are more active bonds, which are mostly participate in the IVR process. And this is a transient absorption measurements of two molecules. So, from the transient absorption, we see that higher nitro component will having faster decay and possible decomposing quickly than amino substituted. The summary is the 1466 and 1990. The CN stretching and CH wagging has uh, uh, more responsible for the energy transfer in IVR process. Yeah, summary of my thesis. So we developed state-of-the-art experiments in our lab, G-scan and foreign mixing and cost characterized NLO materials. The 240 mm cross-section considerably large in case of porphyrins and corals, and from the perovskite nanomaterials, we have studied the broadband NLO properties, and we have observed higher values of NLO parameters. And from the Car's experiments, we of the two tetrazole molecules, we observe that CN stretching and CH wagging is the two bonds which are mainly participate in the IVR process, and other bonds like CN and CC and CH bond tend to decompose very quickly considering its lifetime. And the nitro substituted tetrazole have shown faster vibrase sterilization, and it's at 1.8 picosecond. From the transient absorption studies, we have concluded this, and these are my publications, and thank you.
Yeah. Thank you. Debu, Tirumala, would you like to start? Either of you?
Yeah, yes. Hello.
Yeah.
Hello.
Hello. Yeah, I am
Yes.
Tirumala speaking.
Please.
Yes.
Yeah. Srikanth, I have a question.
Yes.
So you have mentioned cesium bromide perovskite, cesium lead bromide. Some are fluorescent, some are not.
Yes.
Is it because of the synthesis defects, because of the defects, or what is the main reason for that? And how do you control that?
Actually, we got sample from our collaborators. Then we studied this. I am not in synthesis. I'm not sure about that question.
Okay. You just tell me what are the important findings of your entire thesis, which is the new knowledge to the community. You tell me that. And another question is, what is the societal use of these materials? Can you elaborate?
Yeah, these mainly the first part of thesis is the NLO studies, where this we exploring the different NLO activity of this material, which is having different application, as I mentioned in the beginning, which is can be used for mainly the photodynamic therapy and two photon imaging processes. And other part of this is the cars, where this experiment which you can use to study this idea processing and ultrafast Raman studies to uh, illustrate to understand this idea process in any material, organic or inorganic materials.
You tell me one or two points which are the new findings entire from your thesis. What are the important new findings? One or two important findings. Can you tell me that?
Yeah, the from the CAS experiment, it's developing the CAS experiment itself a big project for my thesis, and from this we use this tetrazole, that's energetic molecules, where these energetic molecules decompose very quickly. So we explore this intramolecular energy redistribution process from these energetic molecules. So that is a
Okay.
finding.
Yeah.
Yeah.
Okay,
Debu, you
fine.
want to go?
I have a couple of questions. You have worked with a very exotic system. That part I don't have any problem with. But how do you compare it with very simple systems where you are looking at? So you have stated that you are looking at the end of the day, the IVR aspect of the molecules. And what I could not get, well, because of the short time and all that, is that how many vibrational states do you expect a correlation that you are looking for when you are having the IVR process going on? From the quantum bits, are you able to say that you have, say, 20 vibrational states, 5 vibrational states? Do you have any number?
Exactly, yeah, but we could able to extend it like broadband since we are using a femtosecond pulse, which is having 30 nanometer bandwidth. So we are able to excite like large bandwidth. Like we are
That is
seeing.
okay, but whenever you have quantum
Yeah,
bits, it's because you have a correlation to a finite number of states. Otherwise, there will be no quantum, right? It will just be a decay.
yeah, yes, yeah, yes, yes. Yeah, like we observed like from the quantum bits, like almost 4
That is
to
the
5 drop band, 4 to 5 vibrations will be excited.
okay.
Yeah.
And
Okay.
did that change as you
Any
change
other?
anything?
Debu, go ahead with your next question.
Yeah.
Hello.
Uh,
Hello.
Are you done or?
yeah, it's okay. Fine. I
Yeah.
think it's
So, well, Krishnakant,
Yeah, thanks.
sorry, I want to go back to what one of my colleagues asked. So I never got a feeling what is the big deal about your thesis. Can you tell me? I
Setting
mean,
up
the
the cost.
subject is mature. You have learned, I admit, you have learned many things for the first time. But if it's a thesis, it has to have some. You should feel that there's been a interesting contribution which is different from what was known earlier. I never got a feeling of that, so I'm giving you a chance to say that. In one line, what is the big finding of your thesis?
Yeah, yeah, of course. I mostly work on this experimental aspect, setting up the cost experiment, which I learned a lot working with this
No, no,
ultrafast
no,
lasers.
no. I wouldn't. I
And
wouldn't. I would
the new.
maybe let me rephrase it. See, cars is again 40, 50 years old now,
Yeah,
right? It is true that when you set up, you learn a lot of skills, but the thesis is about new findings which are interesting to the community, and this evaluation is based on what is interesting. So I would like a clear statement from you. There's a chance for you to say, this is the interesting thing that I found from my thesis, which
Ye-
is not known before.
yeah, of course. The experiments are old, and the materials which I have studied is new. So we are studying using the same experiments and studying the new material
No, no,
systems.
but new materials, but what of the new materials? I mean, you put anything, you will get some result. But
Yeah, of course.
where do you place it? You said 10 to the minus 14 is a large, 10 to the minus 14 ACU is large third order nonlinearity. Large compared to what? And you also said confinement effect increases nonlinearity. Why?
Yeah.
Why does it increase nonlinearity?
Yeah, that is studies which theoretical studies which is shown that this confinement is increases its oscillator strength and you expect to have a strong I3.
No, but physically, why? Here he is
Uh,
just saying it's a model, but there's a physical feeling, right?
yeah, there is some theories. Yes, how I
Okay.
can.
So, and why do your DA, pi, A, D, these molecules, why do they have large nonlinearity?
Yeah, in organic molecules with strong conjugation, you have charge transfer between donors to pi bond and pi bonds to donors. So you have strong NLO activity happening in these
But why?
materials.
But why? So what if there's transfer? Physically, how do you
Uh,
explain?
so you have strong dipole moment from this molecular
Why do you have a
systems.
strong dipole moment?
There is a charge separation between
They are
these
highly
two.
polarizable, right? You can move these
Yeah,
electrons. Are they delocalized?
yes, they are delocalized systems.
So they're easily moved around.
Yeah,
That's the
mood around.
reason
Yes.
for their so we'd like physical pictures rather than, I mean, if you just list out several things, we don't get a feeling of what has been the big outcome of your thesis. Anyway, I think we have
Yeah.
run out of time. Anything else? I think Mishraji is there.
There.
SR.
Anyway, most of the questions have been asked, so can we save the time for the next candidate?
Sure. Okay, thank you, Krishnakant.
Next candidate is Dr. Atida BS from ICER, Kolkata.
I'm sorry, I'm not yet doctor. I've just submitted my thesis. I'm waiting for my defense. Sorry for the clarification.
Hopefully, you will soon be a doctor.
Hopefully, yeah.
Right. Yeah.
So with this, let's get started. Good morning, everyone. First of all, I would like to thank the organizers of 30th National Laser Symposium for this platform to present my thesis work. The title of my thesis is Towards Development of New Generation Spin Orbit Photonic Techniques in Observational Astronomy. The work was done under the supervision of Professor Nirmali Ghosh and Professor Dibetu Nandi of IISA Kolkata. So the motivation of this work, the measurement of polarization is usually done using the Stokes polarimetry system. But in dynamical systems such as solar corona, which is the sun's atmosphere, where the activities happen in the time range of 10 seconds to 1000 seconds, it is of utmost importance to measure such polarization states. Why it is important? Because the sun-earth interaction leads to the space weather. The highly charged particles that are erupted during the eruptions from the solar corona damages the spacecrafts out there, which will affect our avionics systems, our power grids, everything. So we cannot prevent these effects or eruptions. What we can do is to predict when this eruptions happens, and timely we can move the spacecraft or avionics system to be shut down at that point of time, or power grids to be shut down at that point to reduce the damage. So in order to produce, you need to know the magnetic field characterization of solar corona or the solar atmosphere, for which you need to have a measurement system which is based on the polarimetry. Now, the polarization measurement of solar corona is very difficult since the incoming photon from atmosphere is very low, and the Stokes V by I signal, which is related to the magnetic field of solar corona, is very low, and there needs to be an amplification of the small polarization system. My thesis also explores the other degree of freedom of light. Apart from spin angular momentum, we also explore orbital angular momentum of light. With this, before getting to started, I would like to have two disclaimers. All the experimental systems that are going to be discussed in the presentation are proof of concept, and it is our future goal to take this to a telescopic backend and do real-time measurement. Even though the applications I mentioned here will be of astrophysical domain, it can be used in various systems such as biology, so complex structures in chemistry, etc. I mean, various light matter interactions. Now, the plan of the talk would be to characterize this polarization corona, because we need to know what kind of signals we are doing the studies on, and we need to have a clue on what is the intensity level of those signals. And second, we'll be discussing the alternative approach to measure polarization. Since it's of high dynamical nature, we need to make up a measurement which is a single shot measurement system. And we'll see how to amplify I'm sorry. Yeah, hi. So how to amplify the small polarization signals, and we'll present the first experimental observation of orbital Hall effect of light, and we'll conclude with future studies. Now, polarization characterization of solar corona. To access and compare synthetic observables to the existing data, and it helps to build an intuition onto how the physical properties of coronal magnetic field structure translate to the observable properties such as the polarizations. In order to facilitate the development of this inversion techniques and to prepare this analyzation technique for a future large telescopic data. Now, in order to do that characterization, we tried to predict the eclipse of total solar eclipse of July 2, 2019. The left one is the white light image, and which was predicted, and right one is the observed image. We predicted this well advanced in 1 month. How did we do that? We have a model at our department SESI where it is data-driven predictive solar surface flux transport model, which will give the measurement of surface magnetic field of sun. And using the potential field surface model, we extrapolate the magnetic field onto the corona. And when we know the coronal magnetic field, we just do the radiative transfer equation to unveil the Stokes parameter using the forward module. From this, we get to know what is the kind of signal, what is the linear polarization, degree of linear polarization, and degree of circular polarization. And degree of circular polarization is related to the strength of magnetic field. And we know that from this study, we know that this the intensity level is of the order of 10 raised to minus 5, which is very weak. So our next goal is to amplify this signal. Before that, let's see how this polarization is measured. So traditionally, the polarization is measured by a pair of retarder and polarizer, project it to different polarization state, and you do different Stokes algebra to measure the Stokes vector IQ UV. Now, why do we need alternative technique? Because the kind of system that we are dealing with is high dynamical nature, and it will require a multiple measurement system. But the time we make the measurements, the dynamical nature have already lost, and it is more more prone to error, and it's not suitable for dynamical system. So now we go to the concept of geometric phase, with which we now conclude how to make a polarization measurement system. The geometric phase arises due to the interaction between the angular momentum of light, and it can be of Pancharatnam Berry phase and speed redirection Berry phase. Unlike dynamical phase, it is not related to path length, but to the polarization change, which is the Pancharatnam Berry phase, or the change in the K vector or propagation vector, which is related to spin redirection Berry phase. Now, in this presentation, I'll be just concentrating on the Pancharatnam Berry phase, which is the change in the polarization state. This is what we know from a homogeneous polarization when it is passed through inhomogeneous medium or anisotropic medium where the orientation axis is space varying, it generates a Pancharatnam Berry phase. Now, when it is projected to different circular polarization, we see a centroid shift and leading to a spin Hall effect of light. Now, this Pancharatnam Berry geometric phase is related to the space varying orientation axis of the anisotropic medium. Hence, the gradient of the Pancharatnam Berry phase will determine how much the beam has to be shifted. Now, we'll reverse this order. We use input as inhomogeneous polarization, which will be asymmetric, and we'll use a homogeneous medium, and this will also lead to a Pancharatnam Berry phase or not. Now, this was our experimental setup where the spatial light modulator was used to generate space varying polarization state by inputting the polarization parameters such as the linear retardance and the optical rotation in terms of the gray level values to the SLM, and it is passed through a half-wave plate which act as the homogeneous medium here and is projected to a circular polarizer, and to different circular polarization you can see the shift in the centroid, and the gradient level that we used into the SLM was this, and which leads to a spin Hall effect of light in the momentum domain. Now, since the space varying polarization was generated using a spatial light modulator, the input parameters that we used were the polarization, axis rotation, or the optical rotation, or the ellipticity. And this was the calculated Pancharatnam-Burry geometric phase, which can be calculated using the Pancharatnam connection using this relation. Now, with this, the SLM input parameters we know. Now, our aim is to retrieve those input parameters from SLM, for which we are going to the polarimetry system here, where we will develop a single shot measurement system. This is a geometric phase polarimeter, where it uses a Mach-Zehnder interferometer. In one path, you have a linearly polarized light. In other path, you have the spatial light varying polarization state generated using spatial light modulator, passed through a half-wave plate, which generates the space varying Pancharatnam-Burry geometric phase, which is imaged onto a CCD. Before getting to the measurement, we need to characterize this Mach-Zehnder interferometer. We measure the dynamical system of the dynamical phase of the interferometer by just putting a constant gray level on the SLM and calculate the dynamical phase. Now we'll change simultaneously or systematically change the gray level pattern on the SLM and calculate the contrast, and which will be related to the optical rotation parameter of the spatial light modulator. Now, after applying a space varying gradient pattern to the spatial light modulator, you have a space varying polarization state, which generates space varying Pancharatnam-Burry geometric phase. From this space varying contrast image, interferometric image, you will be able to extract the phase, which is the total phase, which will be composed of the dynamical phase and the geometric phase, and you will be able to know the geometric phase. And from the contrast information, you know the information on the optical rotation. From optical rotation, that is Chi effect in the geometric phase, you will be able to get the linear retardance value. Now, here we are generating the space varying polarization state using a spatial light modulator by varying the linear retardance and the optical rotation parameter by means of the gray level value. Hence, we are trying to retrieve those to reconstruct the polarization. But in real time, the single shot measurement can be carried out by determining the contrast, which relates to the ellipticity, and dynamical phase and Pancharatnam-Burry phase, which will be related to the geometric orientation angle of the polarization state. So this was the input linear retardance and retrieved linear retardance and optical rotation parameter using this method. And now we move on to amplify the polarization signal. So this method, the weak value amplification or the post-selected measurement, was introduced by Aharonov, Albert, and Weidman in 1988. Standard measurement, we know that the Hamiltonian is represented like this, minus gamma QA, where gamma is the coupling constant, Q is the canonical variable in position or momentum domain, and A is the observable. So in standard measurement, if the position of the eigenvalues are well separated and the positions have been greater than the distribution of the momentum distribution, then at the end of the measurement, we end up with eigenvalues at each point. So you don't have any confusion there. So the distribution that I chose, the pointer to be Gaussian distribution. Now, if the distance between the eigenvalues are small when compared to the distribution of the pointer function, then at the end of the measurement, you end up with a broad Gaussian beam, with the centroid being the average of the eigenvalues. Now, this is a weak nature. Now, how to make measurement in such scenario? You carry out different or many measurement and make out the value of the eigenvalue. Or what Aharonov, Albert, and Weidman proposed was a post-selected weak measurement or weak value amplification system. So here you have a pre-selected system, the weak interaction that was mentioned in the previous slide. The new thing here is the post-selected state, where the post-selected state is nearly orthogonal to the pre-selected state and is projected to this post-selected state after the weak interaction, and we end up with a deflection in the pointer state by a large value which lies far beyond the eigenvalue system. Since this effect is based on interference, yes, it can be realized in classical optical setting. Now, what we asked is it really possible to integrate this concept of weak value amplification with a common platform of interference, so that the weak value amplification of an appropriate weak interaction parameter evolve naturally to the system? for which we have utilized the interferometric weak value amplification of polarization anisotropy, where here the polarization is pointed. Polarization is the pointer, weak interaction is the polarization anisotropy. Here I'll be discussing just the polarization rotation case because of the time limit. Near orthogonal photo selection was done by the path, which is the near destructive interference. Weak coupling is done between the polarization and path degree of freedom. Now, classical field wave will be, in the case of polarization rotation, you have a linear polarization in path 2. Here also the interferometer is, Mach-Zehnder interferometer is being utilized. In path 2, you have the small rotation alpha. So you have real weak value amplification in terms of amplitude offset parameter and imaginary weak value amplification in terms of the phase offset parameter. Amplitude offset parameter reflects in the optical rotation, that is half tan inverse U by Q, and real weak value, imaginary weak value reflects in the Stokes V parameter related to alpha cot epsilon P, where epsilon P is phase value. Now for real weak value, you have this experimental setup. You have a varying neutral density filter. You change the intensity of both the path. In each case, you take the Stokes measurement and calculate the optical rotation. Now you have the optical rotation versus amplitude offset curve, where you have amplified the rotation to 60 times, where this is fitted to a curve called alpha cot epsilon A. Now for phase offset, you have the intensity of both paths to be same. Now you carry out now you take the interference intensity measurement and create a line profile and corresponding Stokes V by measurement and corresponding phase offset value. When it has been plotted, you have a alpha cot epsilon P. Now initially you didn't have any ellipticity, now you have ellipticity. So the density of the measurement was found to be 10 times better. It is 10 times better than the conventional polarimeter from this point, because the alpha that we have used was 0.316 and the delta alpha that we found was 0.008 radian for this approach, and using standard polarimetry the error was 0.02. So it's 10 times better than the conventional polarimeter. Now we move on to the experimental investigation on the orbit-orbit interaction, which is pure, which is not related to polarization. So we know about the Gauss-Angevin shift and the import-Fedorov shift, which is dependent on the dispersion of reflection coefficient and transmission coefficient and the momentum gradient of Bury geometric phase. Here we would like to induce with Lagrange Gaussian beam, and we need to investigate whether it is polarization independent. For which, yeah. So maybe I'll just keep the conclusion and future slides with this. That was the last work that I wanted to discuss. Should I stop the presentation? Hello?
Continue, please.
I think we should conclude now. I think we're done with the time.
Yeah, sure.
Maybe your summary slide, please.
Yeah, sure. So yeah, this is the summary where we have done a single shot measurement system, amplified the small polarization signal, and we explored the orbital angular momentum of light, and provided a first experimental observation of orbital Hall effect of light, which can also be quantified indirectly by interferometric method. Which is independent of polarization. We have also characterized the polarization signal of solar corona to know about the signal that we are interested in.
Next is Jinu from Aralpet.
Okay, thank you. So would any of the others want to start questions? Mishra ji?
Yeah,
perhaps I have one or two questions.
Please.
Yeah. So actually, it is very interesting topic you have described here. I was worried about the measurement of polarization rotation from the light coming from the sun. So actually, you can measure the rotation, that is fine, but in that large distance, how do you get idea of path length so that exact rotation and Burdett constant you are able to measure?
Oh, this is a planar site measurement, right? So this measurement cannot be carried out in a ground space measurement system, because yes, of course, because of the atmosphere, it will alterate everything. So what we are planning is to have a spacecraft, the Aditya mission. We were planning to install this in the Aditya mission, but we have a second Aditya version 2 Aditya mission, which will be out by 2026. I mean, the model will be out by 2026.
No. I think let me
But
just
yeah, I'm coming to
add
the
to the
point.
question. Let me just add to the question.
Yeah.
I think, because the corona is not a single point, it's not a thin medium, it's a huge length.
It's
So how do you
optically
know what
thin.
you are measuring?
It's optically thin.
No, how optically thin? What do you mean by optically thin?
So the radiation is isotropic, and what we'll be doing is we'll keep the instrument outside in the spacecraft.
No,
So
even
the
then,
pathway.
even though you are space based, the point is that unlike in a lab situation where you have a very definite place of interaction, here you are getting first of all the origin of the light and the distance through which it travels.
Right.
How do you know this?
Right. Okay. Yeah, I understood. So what do you mean by is that because of the interaction in between the medium, it can alter the polarization?
No, the medium itself is so huge. I mean, what's the distance of the corona?
Oh, distance of the corona ranges. I mean, we are in the corona. Earth is in the corona.
No,
So
the
we
question is, I think that was intended was what is the length through which it is traveling?
Yeah.
And you're assuming some sort of a uniform worded constant or something, whatever that is for that medium. So how do you take care of all these things? Do you have any standardization?
standardization is till now we haven't gone to that extent, so I cannot answer that question.
No, but other people make measurements too, may not be you. So
No,
how do they
coronal
do that?
measurement has not been done yet.
No, any astrophysical measurement through an extended length of the medium, people measure polarization states. They know cosmic wave background, what its polarization and so many things are measured. How do they do it in astronomy?
So what I know is that they projected different polarization bases and carry out the Stokes measurements by IQUV calculation.
Okay, maybe Mishra ji, you can go ahead if you have any corollary to this.
Yeah, and second thing is that you are doing this budded constant measurement or measurement of Panchratnam phases in lab. So how will you correlate your result to these space measurements? Because one is very small system and other is very large and huge system, and lot of path differences are there, and different turbulent media are there when light is traveling. So how these two things are correlated exactly?
So if we are having a full view, yes, we are dealing with a very much bigger system, but what we in future will be intended to do is that, so what people usually does in sun is that they actually make the measurement at certain points, certain grid points, and they actually photographically stitch the measurement system and give us the measurement of whole surface sun measurements. So here also we will select certain active regions where the eruptions are prone to occur. We'll focus on that region, and yes, those regions it is a magnetic inhomogeneous magnetic field that will be a space varying polarization state. So then we have the homogeneous medium. So the space varying polarization that is coming from that region will be passed to this homogeneous medium that will generate the Pancharatnambari phase.
Okay, fine. Professor Ravin Kumar, I am done.
Yeah. Debu, you have any questions?
Actually, I had a question on your single shot. I mean, I'm not yet clear on what you mean by your single shot, because as far as I understand, you are looking at a continuous light source.
Yeah, so
not
here
but
it's
single shot.
Yeah, so here this is a lab proof of concept. We haven't done any astrophysical measurement jump on this. So in lab proof of concept, yes, we have a helium-neon laser, and you have a linear polarized state in one path and space varying polarization in other path. So you have a space varying geometry phase there. So before making any measurement, you need to characterize the Alexander interferometer. You need to know the dynamical phase of the system. And for each polarization state, you have a space varying geometric phase and as well as a space varying contrast system. Now this each value of this gray level, it will correlate to this optical rotation parameter of the spatial light modulator that we are using, which mimics the space varying polarization state of light. Now, from this
That is a
contrast curve,
very
that will be the calibration curve.
okay. So it's a very slow process. The other quick question is that when you talk about coherence aspects and other things which you are actually measuring as a part of your study, please note that sun, for instance, the coherence aspects of it is very, very low, right? You must know that. And all your studies that you mentioned is subject to the fact that the coherence aspect will be, will undergo a lot of difficulty in that respect. I don't know how you are going to solve that.
Yeah,
That
we
part
are
is not clear.
looking into that aspect currently.
Okay, Tirumala, you have any quick question?
No, it's okay. It's all right. Time is up.
Okay. No, one last thing. You can just comment. What is the weak measurement?
Weak measurement is the post-selected weak measurement system.
No. What is a weak measurement? How do you define a weak measurement?
So you have a weak interaction, okay?
No,
Where your eigen.
I agree. I'm just
In
saying,
general, what is the
a weak
definition?
measurement?
Yeah.
What is a weak measurement?
When you have a post-selected system and you have a deflection which is far beyond the eigen.
Post-selection is for improving on the so-called, I'm just asking, what is a weak measurement? How do you define something as weak or strong?
The position of the eigenvalues, if it is far separated beyond the distribution of the pointer, then it is strong measurement. If it is, the distribution is bigger when compared to the difference in the point of the eigenvalues position, then that is weak.
Okay, thank you. Thanks very much. Yeah.
So,
We
so
admit the next.
let's move to the next presenter, Dr. Jinup from RRCAT. So, Dr. Jinup, can you hear us?
Am I audible?
Yes, maybe a little louder and switch on your video as well and start presenting.
The screen visible now?
Yes, it is. Go ahead.
So good morning, everyone. Myself, Dr. Jinu Bayan. I recently completed my PhD from.
Little louder, please.
Good morning, everyone. Myself, Dr. Jinu Bayan. I recently completed my PhD from Homi Bhabha National Institute, RRCAT, under the supervision of Dr. C.P. Paul, the Engineering Sciences stream. My thesis title is Experimental Studies and Parametric Investigation on Laser-Directed Energy Deposition-Based Additive Manufacturing of Hastelloix thin walls and bulk structures. So this is a presentation plan. First, I'll be introducing the topic and the motivation behind the work, the experimental details, the thesis flow, research works, the thesis contribution, and the publications. So the thesis mainly deals with additive manufacturing, and additive manufacturing is defined as a process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to subtractive or formative manufacturing methodologies. Means we'll be building the components in a layer by layer fashion instead of removing the material and to build a final component. So different stages in additive manufacturing includes, we have a 3D model, which is designed using the CAD softwares or from numerical simulation. And this 3D model is sliced into n number of layers. And for each 2D layer, we generate the toolpath. And then the material addition happens in a layer by layer fashion to build the final component. The major advantages of the technology is the shape design freedom, which it helps to design on print unlimited design freedom, and it's based on feature-based design and manufacturing. Material design freedom means it allows the processing of multiple materials in a single component. Mass customization, it allows customization at the same time and large volume production at the same time. And minimal material wastage because there is no material removal during the process. The most commonly used additive manufacturing techniques for the industrial manufacturing is metal additive manufacturing. And among the different metal additive manufacturing processes, laser-based additive manufacturing is the most common. So the need of the technology is that, so we have laser directed energy deposition based additive manufacturing, which is using a high power laser to create a melt pool onto which the feedstock material is added and the material deposition happens in a layer by layer fashion. It is used for building complex shaped components and lightweight components as well as multi-material components. It can be used for processing difficult to machine materials. And this process, LDED process or laser directed energy deposition process, finds application in aerospace and power sectors. And these sectors is used using the high temperature materials of late to improve thermal efficiency. And the most commonly used materials is the nickel superalloys. The major intention is that this can be deployed at temperature which is greater than 70% of the melting point. So combining these two techniques like LDED and nickel superalloys, we can be able to develop highly complex components for the power sector application. So the major issues involved in additive manufacturing are the process quality, that is cracking and deposit quality issues, microstructural issues, that is non-homogeneity that can occur, the mechanical properties issues, that is deviation from the standards, and the development of complex shape components. So these are the different issues in additive manufacturing, especially LDED of nickel superalloys. So in this condition, we have used three-step procedure. One is LDED of STEC single tracks. Then we went into multi-track and multi-layer deposition. Then we went into the development of a printed circuit heat exchanger for power sector applications. So this is an LDED system that is developed at RRCAD. It's an in-house system which uses a 2 kilowatt fiber laser and a build volume of 250 by 250 by 250 mm cube. It has a CNC manipulation and a dual powder feeding. The material that is used for the study is Hestalloy, which is a nickel superalloy, which is used for power sector application and high temperature properties. It has good mechanical properties at high temperature and oxidation corrosion resistance. There's a reason why this material is selected for this particular project. And the powder that is used for the deposition in this particular process is the spherical powder, which is sized in the range of 45 to 105 micrometer. So the thesis flow, first we start with single track deposition where we have two parts basically. One is track geometry analysis, another is process window development. Then we go to multi-layer and multi-track, multi-layer deposition and go with the wall structures and bulk structures. Finally, go to the development of compact heat exchange. So first work is on the development of single tracks. So first we did the track geometry analysis. We used point heat source equation and extended it to a Gaussian heat source and tried to predict the track geometry. So the track geometry was predicted by using a combination of enthalpy balance approach and mass balance approach. The amount of energy, excess enthalpy that is available in the melt pool is used for predicting the track width. At the same time, the amount of mass balance or the amount of excess mass that is available in the melt pool is also used for predicting the track geometry. With this, we predicted the track geometry and it was found to be very close to the experimental values. Then the track geometry variation with respect to the process parameters were studied and we could see that the track width and track height increases with the laser power, increases with powder feed rate, and increases with the reduction in the scanning speed. The next aspect of the single track is the process window development. This is the most critical aspect because we have three different zones for processing the material. Every material has a different zone of processing where we can get good quality deposition. So this is one zone where we could get discontinuous deposition, and this is a zone where we could get continuous deposition, and the zone where we could get crack deposition. It's mainly because of the higher thermal energy leading to residual stresses resulting in the cracking. So with this, we found that this is a process window where we have to work on to process the material without any defects or cracks. So further, we went into the geometrical studies and the density analysis of the samples, and then we found that these samples are highly dense in nature. So we selected this parameter for this range of parameters for the further studies. So once we completed the single tracks, then we went into the multi-layer deposition, that is wall structures. In the wall structures, we had two different studies. One is effect of LEPF and one is effect of interlayer delay. So it's a typical wall structure built using LDED. So we have walls built one over the other, layers built one over the other, and is built at different LEPF within the process window. So we could see that the variation in the geometry happens along the length and at different LEPF values. And we could see that the stability is more achieved at the lower LEPF values. However, in terms of width, we could see that the width increases with an increase in LEPF, and we could observe a necking phenomena that happens at the lower layers, mainly because of the powder reduction in the powder casting at the lower layers. Then we found the variation in the micro hardness and microstructure, and we could see that the mechanical properties are better than the conventionally built histoloic samples, and a slight reduction in the hardness was observed with an increase in the LEPF values. To correlate these experimental values, we could did a numerical simulation to predict the preheat temperature. That is the preheat temperature on the build surface after deposition of a particular layer. So we could see that with an increase in the LEPF, the preheat temperature increased, which resulted in the reduction of cooling rate, leading to a coarsening of microstructure, leading to reduction in the micro hardness values with an increase in the LEPF values. Further, we did another study where we varied the idle time between the layers. So the idle time is varied between 10 seconds, 20 seconds, and 40 seconds, and we studied the effect of this parameter on the geometry, microstructure, and mechanical properties. So we could see that the geometry had not much of variation, but we could see that more stability is achieved at lower interlayer delay, mainly because of the higher thermal stresses at higher interlayer delay values. And we could also see that the width value reduced slightly with an increase in the interlayer delay. And the microstructural mechanical properties shows that the microstructure is relatively finer with an increase in interlayer delay, and the mechanical properties shows an increasing trend with an increase in the interlayer delay. This is mainly because of the increase in the cooling rate that takes place with an increase in the interlayer delay. So to understand this process, we did numerical simulation again to predict the preheat temperature on the surface so that we can correlate with the results. We could see that with an increase in interlayer delay, the temperature of the preheat surface reduces, which results in the variation in the cooling rates and further results in the variation in microstructure and mechanical properties. Then the next study is on the bulk structures. Bulk structures are structures which are made of multi-track and multi-layer deposition. So the bulk structures are studied where we did multi-track and multi-layer, and then we cut the cross-section and analyze the samples. We could see that the microstructure is columnar in nature with a preferred orientation of 100 plane, and the micro hardness and the mechanical properties were found to be higher than the conventionally built histoloic samples, but lower than the LPBF values, mainly because of the variation in the cooling rates. But with this, we could find that mainly three issues with this. One is the surface roughness, one is the presence of porosity as isolated locations, and non-homogeneity in the microstructure. So with this, we did two post-processing. One is an in-situ treatment and another is an ex-situ treatment. In-situ treatment is a laser remelting where we use the laser to remelt the layers during the deposition. So this helped us to reduce the surface roughness significantly by a value of 70%. And in case of porosity, we could see that in the aspal sample, we can see lack of fusion porosity, and the porosity is significant in the range of 0.5%, which is reduced significantly around 0.01% with the application of SLL. And the grain size was also refined, and we could see an increase in the mechanical properties by 12% and 7% in terms of micro hardness and yield strength with the laser remelting process. Then we did the heat treatment to solve the other problem, that is non-homogeneity in the microstructure, and to achieve properties closer to the conventionally built samples. So we did heat treatment, and we could set 1177 degrees Celsius, which is the preferred heat treatment temperature for the material as per the standards. So we went to the heat treatment, and we could see coarsening of the grains, and we could see that the orientation is random, and the mechanical properties are found to be closer to the conventionally built histoloic sample in terms of micro hardness as well as the yield strength and ultimate strength. Then we went into the process methodology for LDED of compact heat exchange. So we developed this methodology. We developed the process window for processing the material. Then we studied the material properties, that is the microstructural and mechanical properties. Then we studied the geometry and surface analysis, that is where wall structures are studied, the overhang walls were studied, bulk structures were studied. All these parameters entered into the development of a printed circuit heat exchanger, a prototype printed circuit heat exchanger for the power sector applications. So this is the strategy that we use. We use a 3-axis LDED system for this particular work. And the major issue is that whenever we deposit the wall and try to deposit a solid deposit on top of it, it tries to collapse, mainly because of the gravitational effects. So because of that, we use overhang walls and we try to join to the top layer and we try to make a channel out of it. So with this, we did the trial experiments and we could find that the maximum shift that we can give is 15% of the track width for preventing the collapse of the walls. Then Further to this, when we could make the channels, we went into the development of single layer channels as well as the development of a prototype heat exchanger. So we developed this using this technology, using the developed process window, we developed the prototype heat exchanger using an LEPF value of 10 kilojoule per gram for the wall structures and 12 kilojoule per gram for the bulk structures. So the contribution of the thesis is that it comprehends and contributes to the existing understanding on LDED of airstrike structures from single track to multiple overlap and multi-layer tracks. Studies are done under different process conditions, yielding thin walls and bulk structures in terms of processing, geometry, microstructural, and mechanical properties. The study on physical treatment and exitive post-process and study contributed to the development of a process methodology for building printed circuit heat exchangers using LDE. The academic outcomes of the thesis is that we have 8 journal publications published and 2 which is to be communicated, 2 book chapters and 5 conference papers. These are the total publications during the PhD tenure. And I thank the organizers, my supervisor, funding from DAE, RRCAT, SBNA during my PhD, Team Laser IT Manufacturing at RRCAT, doctoral committee, scientific officers at RRCAT for characterization facilities, collaborators at IGCAR and DSSC for the study. Thank you for your kind attention.
Okay, thank you very much. Just like to ask you, so is this going to be a universal process, this 3D, this additive manufacturing that you said, or is it applicable only to certain kind of materials?
It can be used for many materials. We have used for processing different grade of materials, which includes iron grade materials, titanium based, nickel based alloys. So different grade of materials can be processed.
Yeah, but you know, I mean, having said this, since you're doing it layer by layer,
yeah,
it's extremely time consuming.
It is time consuming if you compare with the conventional thing. Then at the same time, if you compare with the total product cycle, it is less. Means if you compare the production that happens by the by purchasing of a raw material, then removing the machining, removing the material by machining, or the process planning that is involved in the conventional manufacturing, the total lead time or the total process time is less as compared to conventional manufacturing.
But suppose once you have an established thing, then so I'd like you to bring out the unique features of this process versus the conventional process.
This is mainly used for baking components that are very complex in nature, which as I mentioned in my initial slide, the major freedoms offered by the technology are the shape design freedom. So it is, if the component is very complex in nature, then additive manufacturing solution, because in conventional manufacturing, as the complexity of design increases, the cost of the component increases. While in additive manufacturing, it is not a function of complexity in design.
What about post-processing? I mean, for example, what about the stresses in the manufactured piece? How does it compare in both the systems, both the methods?
We have to do the post-processing. That is the third stage in additive manufacturing. So there are 3 major stages where in the methodology, there are 3 different methodologies. One is pre-processing, where we get the 3D model. Processing stage, where we make the processing of the component or the building of the component. And post-processing is the final stage where we try to customize as per the requirements of the customer. Like we can
that's different, but I'm talking about things like which are stresses, you know, in conventional machining. For example, I can say that there can be lots of stresses in the machine material.
Yeah.
Which takes, so what about in the 3D, in this additive manufacture?
Yeah, tensile stresses are mainly seen on the surface, but residual stresses is a bigger concern because of the continuous thermal cycling that happens during the process.
Okay.
It is avoided by using post-processing techniques.
So is it likely to replace conventional machining in some future?
No, it is not going to replace, to be frank, but it will be working along with conventional manufacturing. It won't be able to replace entirely, because additive manufacturing is again combined with conventional manufacturing, which is known as hybrid manufacturing, where we do additive manufacturing during a deposition, we do machining. So it works along with conventional manufacturing.
Yeah. So let me invite my colleagues if they have any questions. So Debu, Tirumala, Mishra.
Yeah, Juno. Hello.
Yes, sir.
Yeah.
Yeah, you have mentioned you have made some heat exchanger. Have you done any measurements on that performance of heat exchanger?
No, sir. That is the future scope of the work. The final end goal of my thesis was to develop the methodology for fabricating the heat exchanger. But we did some analysis which shows that the channels are open at both ends. So there is no closed channels. The channels are open from both the ends. That is only the analysis that we have done.
But see, additive manufacturing, when you do laser deposition, the walls which are deposited are relatively very highly rough in nature. So how do you do machining? Because if it is being done at external wise, you can do by any mechanical means. But inside this kind of structures, because that will be one of the killing factor of the performance of the heat exchanger.
So for that, one of the techniques that can be used is a slurry-based machine, where we pass the slurry through the channels, and we can be able to clean the channels, and we can improve the surface quality.
Okay, then see, what about the current status? Because additive manufacturing is going on so many years. Nowadays, other than laser, there are other means of additive manufacturing process are commercially available. With respect to that, what is the laser-based additive manufacturing advantages, why it is, and what is the major contribution of your thesis work?
Yeah, the advantage of laser additive manufacturing over other is the precision that it achieves instead of like other techniques like wire arc additive manufacturing, where we use a larger beam diameter which is used in the welding. So where the surface quality is bad and the beam minimum feature size is also less. So that is a major factor in terms of additive and the quality of LIM. And in terms of the contribution of thesis, the major contribution of thesis is that it gives a proper understanding on the properties of the material. Like first of all, the processing of the material, there is no understanding so far on the processing of this particular material, where what are the process parameters used for the processing of this material. At the same time, there
No,
was no
that is
understanding.
what actually I want to say. Can you pinpoint that? See, the work is going on so many years. From your work last 4-5 years, whatever you have done, what is the new knowledge you added to this laser additive manufacture sector?
Yeah. So the major thing is that the process window that development, that is one part for this particular material which has a high cracking tendency. So one of the major issues in additive manufacturing is the development of process window for crack sensitive materials. So we have to have a very close process window for developing this sort of structures. So that is one part. Other part is this process methodology that we develop, because there is very limited studies across the globe for fabricating such a large structures using DED technique based additive manufacturing. So this is a major one of the major.
Zinub, sorry to interrupt. Can you elaborate on process window? What does it refer to?
Process window refers to that zone of process parameters. Like we have different process parameters in LIM, like laser power, scanning speed, or powder feed rate, and beam diameter. So we have a particular range of process parameters which can be used for the continuous deposition and defect-free deposition of a particular material. So this process.
A related question is that whether laser intensity or pulse duration do matter for developing the good quality surface, or how does it reflect on the surface cracks?
Surface cracks, if the laser power increases, laser intensity increases the thermal stresses in them, because it increases the thermal gradient. Then we increases the thermal stresses on the surface, which leads to cracking.
And so what way it reflects on the material parameters, the selection of material, whether you take nickel or zirconium or steel?
It depends. That's why the process window development is material specific. So we have to develop there based on the material properties. We have to develop the process window for each and every material. Like in the conventional, we have machining parameters for each and every material, different aluminum, steel, or copper. We have different processing machining parameters. In additive also we should have.
See, conventional bulk versus this additive manufactured piece. What is the difference in strength?
Strength is higher than the conventionally built samples in the as-built condition because of the finer grain structure and the higher dislocation density. But the ductility is poor, so we try to do heat treatment and the post-processing to improve it further.
Okay, Debu, you have a question?
Yeah, just quick question. You know that for the laser machining, the regular laser machining, not the additive subtractive one, as you go to shorter and shorter pulses, the mechanism changes, and often the machining is much nicer and smoother because it goes into the plasma mode of operation. Do you see any difference in terms of mechanistic change as you go with different different laser pulse widths?
Yeah, because we generally use continuous wave lasers for this additive manufacturing purposes. We don't use pulses.
Okay, it was just curiosity. Thank you.
All right. So thank you very much, Jinu. So
Thank you, sir.
let's move on to the next one.
So our next presenter is Dr. Samuel Nalam from University of Hyderabad. So Dr. Samuel, can you hear us?
Yes, sir. Can you hear me?
You please start. You present yours.
Louder. Please stick to the time, huh?
Yes, sir.
Yes. Okay, share your presentations. Maximize your screen. Yes.
Good morning.
So start.
Yes, sir. Good morning, everyone. I am Amil Anurag. I will be discussing the work that I have done during my.
I think you have to speak little louder.
Okay, sir. Can you hear me, sir?
It's very low.
How is it now, sir?
Yeah, it's better. Stick to this, yeah.
Yes, sir. So I'll be discussing the work I've done during my PhD on femtosecond pulse propagation in air towards filamentation nonlinear optics. So the outline of the talk would be, first I would discuss the background and introduce filamentation. Then I will talk about the briefly the instruments that I have used. And then we will do a holistic analysis of the filament and the different emissions that it produces by varying different pulse characteristics. Then we will see the third harmonic generation and supercontinuum generation from the filament and the enhancement and our new findings that we have reported. And then we are going to see the acoustic emissions from the filament. And then we will be moving on to looking at the RF emissions from the filament at the same time. Since all of this work was primarily done towards application in remote sensing, we have done some preliminary experiments towards detection of some solutions and aerosols in the lab.
May I suggest you focus on one or two of the main themes, please? It's too long otherwise for 13-14 minutes.
Yes, sir. Yeah. Yes, sir. So filamentation, which is a dynamic interplay between the Kerr cell focusing and plasma defocusing, which gives a beaded spatial plasma, which propagates over multiple, many orders more than the Rayleigh range. And why we want to use this for remote sensing is because it has an intensity of an order of 10 power 13 watt per centimeter square, which can be generated, which can be made at a very far off region. And at the same time, we'll be having a spectral broadening or supercontinuum emission, which has a sometimes has a broadband distribution of about an octave, which we can use for probing of remote materials. And also at the same time, we are having a terahertz source and from the filament also. While also being able to create this plasma channel, we are also, people have reported being able to guide lightning discharges. So to move on in this direction, I have first we try to first simulate this filamentation starting from the the Maxwell's equations. And by since this equation cannot be solved, we have made a few assumptions like cancelling the vectorial effects and shifting to from the pulse frame to the laboratory frame to the pulse frame. And we have done the paraxial approximation and the slowly varying envelope approximation. And we arrive at a canonical equation which looks like this. So with this particular model where we are considering Kerr effect and multiphoton absorption using the Crank-Nicolson scheme, we have done some preliminary simulations. So when we did the simulations, we are able to see that the pulse moves back as the filamentation moves back with the increase in energy, which is what is expected. And we are also seeing the lobing pattern. But there are some things which we are not able to show in the simulation, which are we are not able to simulate shorter focal length focusing geometry, and at the same time the intensity values are an order lower than what was measured in the experiment, and we are not able to simulate distortions in the wavefront or the temporal duration of the pulse. So we need experimental support. So crudely speaking, the work was done using a short pulse amplified TSFR laser, and there were some pulse modifications that are put into it, like polarization, power, chirp, pulse duration, and then the pulse is characterized using a single shot autocorrelator, spectrometers, and power meter, and we generate the filament in air or aerosols, and then finally we characterize these emissions using spectrometry, sonography, and RF analysis. So largely the spectrum was taken to estimate the intensity of the filament and electron density of the filament. The intensity was estimated using two different nitrogen lines in the filament, and electron density was estimated by the Stark broadening of the oxygen 845 nanometer line. According to the requirement, we have used three different spectrometers according to the repetition rate needed and the gating that was required. And we have taken images of the filaments using CCD cameras and DSLR Nikon T4i camera according to the resolution and the spatial extent of our imaging. And we have also done some acoustic analysis. This is what a typical acoustic signal from a filament looks like. From this, we try to extract all these quantities such as peak-to-peak pressure, arrival time, the frequency distribution, and the length or the burst length of the pulse. This is a microphone that we are using. And for the radio frequency characterization, we use antennas coupled to the spectrum analyzer or an oscilloscope. And we have also used a single shot autocorrelator to measure the pulse profile. And here we are showing for the shortest transform limited pulse from the laser, we are able to get made a calculation of 63 femtoseconds. And since we are also doing work while varying the chirp of the input pulse, we try to characterize the chirp induced by the grating separation. So with the different steps of grating separation, this is the pulse duration and the chirp that is induced. So we now move on to the complete spectral anatomy of the femtosecond filament, where first we want to keep everything constant and see how the filament changes its focal geometry and input power. So if this is the initial pulse profile, we are primarily changing these two quantities here and keeping everything else constant. And once we move from increase the focusing length of the lens used to generate these filaments, we find we went from 50 mm focal length to 1000 mm focal length. We find there is a sudden shift in the spatial extent when we go from 300 mm to 500 mm focal length with the laser that we are using. And even when we are doing the intensity estimation, which we are able to do only up to 1000 mm using spectroscopic techniques, we find that with 1000 mm the variation above 300 mm, the variation in the intensity with the same variation in input pulse energy is much lesser, like 5 terawatts. While with the lower focal length lenses, we are observing a variation of about 20 terawatt per centimeter square. So using this information, we are making this classification saying that there's tight focusing and loose focusing conditions, which we will be using through the course of the thesis. And we have seen what aberrations do to the filament as well. So we have used different focusing optics with the same focal length, but different materials and dimensions. So the main things that we found that influence the filamentation, the aberrations that influence filamentation are pulse to phase front delay, chirp, and spherical aberration. Even the pulse to phase front delay and the chirp also are separated into overall, that is induced, and the radially varying component. So, and this we have calculated according to the dimensions of the different focusing optics used and the material that was used. So we find that and we have used 5 different optics. One is an off-axis parabolic mirror where we have the least number of aberrations and only that which will arise due to alignment flaws. And we have used the achromatic doublet, which doesn't have any radially varying component but induces a large overall choke. The rest of the other 3 lenses induce radially varying components, but they reduce a little of the large overall choke that is being done. So now, how do we choose which element to use? If you want higher electron density, do we use the off-axis parabolic mirror just because it has the best focusing conditions? We find that when we take the intensity profile, this is what the spectrum looks like along the different positions of the filament, and we find that there are 2 main classifications of the filament where there is a 3 centimeter filament under the same focusing geometry and a 1 centimeter filament under the same focusing geometry. And the filament is shorter, especially in cases where there's a radially varying component. So we are saying that the filament gets cut short because of the early termination of the filament because of the radially varying component. But we also find that the electron density of these radially varying component filaments is higher compared to the electron density that was found for the achromat or the off-axis parabolic mirror. This is because of the early termination of the filament. We observe higher intensities. So we can see here that how aberrations can increase the intensity of the filament. But when we try to look at the supercontinuum that is generated, we find that the off-axis parabolic mirror has the lowest minimum wavelength, or the best supercontinuum that is generated. This is because of the longer length and the comparable electron density. And the achromatic doublet has, although it has considerable length, it is very low in electron density and intensity, because of which we don't observe strong supercontinuum, whereas other three lenses show similar supercontinuum generation. And we have also varied the chirp of the input pulse. With these aberrations, we see firstly that when we are using an off-axis parabolic mirror, the zero chirp is where we get the best supercontinuum generation. But whereas when we move on to the transmittive optics, we get the best supercontinuum generation for positive chirp values. This is because when there is a positive chirp value and a pulse to phase front delay, the pulse shifts towards the Brewer frequencies for positive chirp, because of which we observe a slight increase in the supercontinuum generation or decrease in the minimum wavelength. And here we have used a lens combination with chirps to see how far we can vary the onset of the filament. So we are able to generate filaments between 0.3 to 3.5 meters just by using a combination of lenses and varying the chirp. And we are also seeing what will happen to the filament with lens tilt. With lens tilt, we are able to cut down the large amount of fluorescence that otherwise happens when we purely focus the lens. And we are also treating this current lens tilt effect as a chromatic aberration instead of how usually people treat it as astigmatic aberration, where there is a difference in the tangential and sagittal focus. And here in the supercontinuum variation with tilt of the 150 mm lens, we see a sudden spike in the supercontinuum generation at a tilt angle of 7 degrees. This is because there is a interaction between the two filaments that form, and there is a sudden increase for supercontinuum at this position. And we want to look at the third harmonic generation from femtosecond filaments. And as this intense femtosecond filaments have third order effects as well, and multiphoton ionization. There is third harmonic generation, self-phase modulation, and Kerr self-focusing. Kerr self-focusing with multiphoton ionization gives us filamentation as explained. And from the third harmonic generation, we are able to get a coherent UV source when we use an infrared laser. And also we observe, because of self-phase modulation, supercontinuum generation gives us a coherent white light source. As both of these can be very effective if properly applied for remote sensing, we are working further on it. So these are the primary terms that we are seeing. So what is the main problem when we want to generate a third harmonic generation? It is firstly phase matching conditions, and second the Goy phase destructive interference. But in our case, we are getting phase matching due to the cross-phase modulation of the third harmonic generation by the fundamental, and also by the development of the plasma, which alters the refractive index to achieve good phase matching conditions. So because of this, when we change the intensity, there will be a particular when we change the pulse energy, there will be a particular pulse energy value where we will be getting the best third harmonic generation. So this is how the refractive index changes with the process modulation focusing for best phase matching conditions. And these are our so here we are seeing a typical SEG supercontinuum and third harmonic variations, where we are seeing best third harmonic and supercontinuum for elliptically polarized light. And with chirp, we are able to suppress the supercontinuum and see third harmonic generation. And at this particular chirp value, there is a sudden drop in supercontinuum and sudden increase in third harmonic generation, which shows a exchange in energy. With ellipticity, we are able to see best third harmonic generation for long focused conditions and an elliptical polarization. And with lens tilt also, we are able to see a 2.5 times increase in the third harmonic generation at an 8-degree angle. This is because of the interacting filaments. And we are also able to tune the third harmonic that is generated by lens tilt and varying the chirp by about 20 nanometers. And we are also observing acoustic generations from the filament. There are optical emissions which we have characterized earlier, and there is the acoustic signals which we characterize by the microphone. And as I have discussed earlier, we are talking about peak-to-peak pressure, arrival times, burst length, and frequency distribution. And we are able to detect filaments where we are not able to visibly observe the filament, we are still able to observe the filament using acoustic analysis. Acoustic analysis can be a very rugged characteristic tool towards filamentation, as they are able to detect weak filaments and also are inexpensive. And they have a direct correlation, the peak-to-peak pressures have a direct correlation to the electron density that is observed. And when we try to see the burst lengths, for the 500 mm lens generated filament, there is a difference in the burst length, which is not linear. And when we do a further frequency analysis, we find that there are multiple frequency components that arise at the peripheries of the filament. This is because of multiple filamentation, which we don't observe at the 2000 mm lens, which has a uniform profile. We have also observed RF from the filament.
I think we should conclude now.
Yeah, yes, sir.
Are you just going on with a variety of results, which we might lose focus?
Yes, sir. We have looked at the different emissions from the filament, and finally we are applying it to. This is the final one, sir, where we have done some preliminary application, and we are looking at the fibs that we are seeing, and we are also seeing the 2-photon absorption from riboflow even using the filament. All we have detected this from 1.5 meters using our basic spectrometer and camera lens. And since we are using 266 for third harmonic generation, I'm here showing different explosives and dangerous chemicals that can be detected using this, sir. And we have also used acoustic analysis to find the tryptophan particle concentration in our solution. And we have also done some material damage on aluminum. And
yes,
yeah.
Perhaps we should end here and talk about, I mean, let's discuss. Yeah.
Yes, sir.
Is that okay?
Yes, sir. Yeah.
Yeah. So, are there any questions?
Yeah, Samuel.
Yes, sir.
So, what is the mechanism of filamentation?
Yes, sir. So, at these high intensities of femtosecond pulses, where there will be a refractive index change, which is defined by the spatial profile of the laser pulsar. So, because of that, it will have a lens-like effect.
No. You tell me the material interaction point of view. What is the origin of filamentation?
So, filamentation is basically like a long propagation, which is caused due to the self-focusing and plasma defocusing.
No. What is the origin of filamentation? The question.
Origin of filamentation, as in what causes?
Why does filamentation happen?
So,
yeah, yes, sir. So when a laser beam gets focused, there will be
what is the intensity levels it is required? Minimum threshold intensity is required for filamentation.
It is 10. Like if in air, it should be about 10 gigawatts per centimeter square.
What does 10 gigawatt per? Who decides that?
We calculate according to it's like the critical
No.
power.
What happens at that intensity? What happens? Material, what actually it will see?
Okay, so when we normally propagate a laser, it will have a diffraction length, sir. It is supposed to it is supposed to diverge. But at a particular intensity,
No. You don't worry about nonlinear interaction. You suppose if I give that much intensity or more than that, if I give somehow.
Yes, sir.
So after focusing, your intensity will increase. But at that time, at that intensity, what is happening inside the material?
Okay. We are seeing higher order polarization effects, sir, in the material.
Okay, then what happens?
Yes, sir. Continue, sir.
So what I am asking, can you do the filamentation in solid materials?
It depends on what is the absorption that the solid is.
No, same intensity. I have subjected the laser intensity a gas and a solid.
Yes, sir.
Can it filamentation can occur in both the media, or is there any issue in that?
Sir, but it will occur at different spatial extents. The length of the filament will vary, sir, because of different absorption mechanisms and energy dissipation mechanisms.
What is that mechanism? That is what I am asking.
Okay, so in air, it will be like the main ionization mechanism is multiphoton ionization, sir. But when we are moving to solids, it will go to inverse Bremsstrahlung and other kinds of ionizations where
what are other ionizations?
I think maybe we move on to a different question.
Okay, it's fine, fine. Now you tell me, there's a supercontinuum sources are already available commercial market.
Yes, sir. Yes.
With respect to that, what is the new findings of your thesis work? What is that?
Yes, sir. Compared to those supercontinuum generation, the supercontinuum generation that we are doing here is less actually. But here we are able to generate the supercontinuum in a remote region, sir. Like in a region of interest. We are not generating supercontinuum near my laser, but in a far off region, we can generate the supercontinuum. That is the main advantage of this generating supercontinuum in filamentation in air.
Okay. So, Debu.
Very quick question. Yeah. So when I still didn't get it. Your laser that you are using, is it an amplified laser or an
It's an amplified chub pulse amplified laser, sir.
So you are looking at the effect of a amplified laser with different chirps and its filamentation.
Yes, sir.
Right?
Yeah. Chirp is one of the things that we are wearing, sir. Yes.
It's okay. But this is a very old kind of, something which has been going on.
Yes.
What we are struggling to understand is that what is the new thing that you have done?
Yes.
Which makes it unique? Is there anything that you can say?
Yes, sir.
On that.
One of the main things that we have done, which we have already also applied for the patent, is where we are generating the third harmonic from the filamentation, and also we are enhancing it, sir. Enhancing the third harmonic that is generated during filamentation. So we are able to generate a UV in a remote region again, according to our region of interest. So, and we are able to tune it at the same time. So, yes, this is one of the things. Like, yes, sir.
Okay. Yeah, I think we have finished the time. So maybe, or you have a question, Mishra ji?
Yeah. One small question. You see the third harmonic generation. What about other harmonics? How they are suppressed or why they are not there?
I mean, like with our intensity that we have, we can go up to the third order susceptibilities. So that's why third harmonic, but we don't observe second harmonic, obviously, because air is like a centrosymmetric medium. Like it is like we don't observe second harmonic at all when in comparison to the third harmonic that is observed.
Okay.
Okay. Thank you.
Thank you, sir. Thank you.
Yeah. Judges and session manager, can I take a 5-minute break, physical break? Is that okay? We start in 4 minutes.
Yeah.
Please allow the other person in. And
Sure.
just take a toilet break. Thank you.
Okay.
मोनोबिना आ गई है so just बोलिए कि we will take a break for 5 minutes.
Monobina, can you share the slides?
Yeah. Is it visible? Hello? Is my screen visible?
No. Right now it is okay.
Okay.
So full screen mode. Yes. Fine. Can you just speak out whether your voice is audible? We would check.
Yeah. Hi. Hello.
Yes.
Okay. Thank you.
Okay, it's fine.
We
We will wait for a few minutes.
Yeah, sure.
Judges is just coming after a break. Maybe
Yes.
2-3 minutes.
Okay, sure. Thank you.
Yeah, thank you. Can we start?
Okay, sir.
All the judges are there.
Uh,
Yeah, you
all,
can.
all
You can.
other
Yeah.
judges are there.
Yeah.
I am here. Yeah.
Yeah, sure,
So
sure.
okay,
We are here.
so we'll move to next presenter, Dr. Manovina Karmakar from IIT Kharagpur. So, Dr. Manovina, can you just start presenting?
Sure. Thank you, sir. Good morning, everyone. I'm going to present my thesis. Title of my thesis is Ultravast Quasi-Particle Dynamics in Layered Transition Metal Dichalcogenates and Other Metal Monochalcogenates.
Just can you hear her?
Yeah, we
Hello?
can hear.
Okay, fine.
Yeah. Can you just highlight your thesis, please? Don't go through everything that you have done. That takes a long time.
Sure, sir.
Just the highlights.
Yeah. Okay, sir. Thank you. So here's the contents of the thesis. So first I'll introduce to the topic, and then briefly I'll move over to the experimental methods and data interpretation. And in the next 4 chapters, I describe the 4 different works on quasi-particle dynamics in transition metal dichalcogenates, precisely on excitons, exciton plasma interactions, tryons, and photo-induced carrier dynamics. And next I'll conclude. So transition metal dichalcogenates are a class of materials with general formula of MX2. So where this M is a metal atom and X is a chalcogenate like sulfur selenium. So these are very popular two-dimensional materials. So two-dimensional materials are they have this weak van der Waals force in the Z direction, so that one can separate one layer from the other using different exfoliation techniques like scotch tape exfoliation, which is a mechanical exfoliation, and there are other exfoliation techniques. So these materials have gained a lot of interest due to their different optoelectronic properties. For example, these sub-nanometer thick materials can absorb around 10 to 20% of the incident light in the linear absorption regime. And this kind of semiconductors undergo indirect to direct bandgap transitions, while we reduce the layer thickness from a bulk to a monolayer limit. Due to this reduced dielectric screening in this material, there are different quasi-particles observed in this range of materials like excitons, tryons, biexciton. And due to these optical properties, there are various applications like in photodetectors, field effect transistors, LEDs, solar cells, etc. So now, like I said, these quasi-particles are a group of interacting particles formed after the light-matter interaction in a semiconducting material. So exciton is an electron-hole pair. Tryon is a 3-particle charge entity where there is 2 electron and 1 hole, or 1 electron, 2 holes. And biexciton is a charge-neutral 4-particle identity. And electron-hole plasma is Coulomb-correlated many-particle state. So the main objective of the thesis is as follows. So these bulk 2D bulk transition metal dichalcogenates, they have very strong screening and weakly bound quasi-particles. And on the contrary, in the monolayer limit, they have very weak screening, and so the excitons and other quasi-particles are strongly bound. Now, what we want to study is that what is there in between, where we have moderately bound excitons and we have moderate screening. So this screening enables different tunability in these quasi-particles that we will explore. So basically, we explore the evolution of quasi-particles upon light-matter interaction in time, and in other transition metal dichalcogenates, and in other successors of this material. So importance of these are reflected in optoelectronic device applications. This provides efficient tools for efficient device engineering, and also it unravels fundamental many-body physics in these semiconductors. So we use 50 femtosecond 1 kilohertz 808 nanometer regenerative amplifier as our master laser. And we use optical parametric amplifier, where we get tunable output from 240 to 2.6 micron. So as a experimental tool, we use transient absorption spectroscopy. So as we know, this is a 2-beam technique where we excite the material with a pump pulse, and we observe the absorption with a weak probe pulse that comes after the pump at several delays. and we detect it in the spectrometer. So I'll not go through the details of the setup. So basically here this is the master laser. We have optical parametric amplifier, and this can tune the pump wavelength, and as a probe we use the white light supercontinuum generation from a nonlinear optical crystal, and we measure the time dependent absorption. So I'll directly move into the third chapter, observation of dynamic screening of excitons. So excitons are an analog of the hydrogen atom, where this electron hole pair are bound. So these bound states lie just below the band continuum as discrete states. So these are the discrete energy. It varies like this, and the binding energy of an excitonic state is directly related with the dielectric permittivity. So now this is inversely proportional with the binding energy. This is called the effective dielectric permittivity of the exciton. So if one can tune this permittivity through some external inputs, one can change the resonance energy of the excitons, and hence they can change the device properties. So the one important parameter is the screening of the Coulomb interaction in an exciton. So excitons can be screened by the environment, so where electron hole plasma or other quasi-particles like trions or biexcitons or other free carriers can contribute. So basically the dielectric function is a function of frequency. But if we see this equation, this is not a function of frequency, rather this is just a number. So now the question that we ask is here, that how this frequency dependent quantity is related with this constant number that dictates the excitonic binding energy. Now there are several studies, basically theoretical studies, that predict that there could be a characteristic frequency or a set of frequencies at which the excitons are effectively screened. This is a prediction, but usually some studies approximate screening through the dielectric permittivity either at optical frequencies and or at the static frequencies, and none of which exactly matches with the experimental results. So here we try to find these characteristic frequencies. So we use a transistor metal dichalcogenate MOS2, and which shows excitonic absorption peaks, and it is an atomically thin, so thickness is around 12 nanometer. We use pump probe geometry. Basically we observe the time dependent absorption of these excitonic peaks. Now after photoexcitation, the absorption reduces in this excitonic features, but interestingly we observe that this first excited state, which is known as 2S state, absorption increases over after the photoexcitation. So this is an aberrant result, and to find this origin, we employ this Kramer-Skornik analysis and find the change of the dielectric permittivity over time. So we observe that this 2S exciton state, the permittivity at this resonance it undergoes some reduction. So due to this reduction, we observe this enhancement. Now we propose the following model to relate the environmental dielectric permittivity, which is a function of frequency, to this with this effective permittivity, which is just a number. So with this model, and we put some additional constraints, like some assumptions that the screening is effective at the resonance. So here we are looking at the 2S exciton, which is the first excited exciton. With this assumption, we reproduce the absorption oscillator strength enhancement of the 2S excitonic state. So now the main findings from this study is that these 2S excitons are screened via the 1S excitons, and mainly this exciton screening is effective at the excitonic resonance. This is the main finding of from this study. So here we introduce the hypothesis that efficient screening at exciton resonance, and from our experimental data it matches, and we say that excitonic resonance is a characteristic frequency at which environmental polarization effectively screens the Coulomb potential. So this is our first ever experimental demonstration of the dynamic screening. So next I move on to the next chapter, electron hole plasma formation dynamics in transition metal dichalcogenates. So electron hole, as we know, electron hole plasma is a many particle state constituting of free charge carriers that are correlated via Coulomb potential. Plasma frequency is related with the square root of this n, which is the number of charge carriers present. And the main criteria for plasma formation is this: omega p tau, omega p pl times tau is much greater than 1, where this tau is some time of carrier scattering or other damping time. So basically this plasma formation period, basically this plasma oscillation period has to be much slower compared to any damping time in the system. Otherwise this plasma cannot sustain in the system. So in 2001, Rupert Hoover and their group, they have shown that this plasma formation time in a semiconductor is of the order of the inverse of the plasma frequency. Now this study was performed in gallium arsenide and at a particular excitation density. So now what we want to do, we want to change the excitation density and want to see whether this follows. So we are basically tuning the plasma frequency and want to understand the plasma formation time. And of course we are studying this in a transition metal dichalcogenate and in a different system than it was done before. This is just a cartoon schematic of what we want to see: transition of uncorrelated electron and holes to this correlated electron hole plasma. So we use transient absorption spectroscopy in optical pump, optical probe mode. And to detect this plasma, we trace the plasma screening in the excitonic spectrum. So now first we need to understand, we need to distinguish between free carriers and the correlated carriers, which is the plasma. So for that we track this oscillator strength reduction, which occurs due to the free carriers, which may be uncorrelated or correlated. And we track the excitonic redshift over time due to the band gap renormalization. Now band gap renormalization comes only when this plasma is formed. So we will not be able to see any redshift if the free carriers are not correlated. So we'll compare these two conditions and distinguish this plasma. So this is the again MOS2 system. So there are 4 excitonic peaks. Here we choose the C exciton, which originates from the parallel valence and conduction bands here. And this is the model that we consider to find out the temporal evolution of different excitonic parameters, mainly this absorption oscillator strength, resonance energy, and the line width. So over time, we use this model to find out parameters. So next, I'll just briefly tell about this oscillator strength dynamics first. So this oscillator strength dynamics is dictated by a second order equation. So dn dt proportional to n square. So that's why this inverse of the carrier dynamics is follows some linear relation. So sorry, should I? Hello.
So continue 3 more minutes.
Okay.
Wind up.
Thank you. We compare this number of carriers that participate in the oscillator strength dynamics, and from this resonance energy renormalization, we compare this number of carriers that participate in this screening. Electron hole plasma formation. So with that, we find that only 1 to 3% of the injected carriers form the plasma and contribute to the band gap renormalization. Next, we vary the carrier density and observe that the plasma formation time first reduces and then again increases. So at certain level, it follows whatever Hoover had predicted, but after a certain threshold, it does not follow because here this carrier scattering time becomes very fast. So these are the main conclusion from this chapter. Now I'll just briefly move over to this. Here we study this strand formation dynamics through pump probe technique, where in steady state we for a trion we have some doping and we excite an electron hole pair. But in pump probe, through pump we excite some carriers, and through probe we excite another pair, and it forms a trion. So here we observe the time dependent evolution of a trion feature, and from that we measure this carrier temperature over time, and this we could track the quasi-Fermi levels and its evolution over time. And okay, I'll briefly go over to this next chapter, which is photo-induced carrier dynamics in a 3,6 metal monochalcogenate system, which is a gallium telluride. So this is the next. This is the successor of transition metal dichalcogenates. So these materials have been found to show very high photo detection capabilities as compared to other 2D materials. So in this chapter, we try to understand the reason behind this. So we study the carrier dynamics, and
Yeah, I think we should conclude now. Your time is up.
okay, I'll just conclude. So I'll go to directly the chapter
Please,
conclusion.
please.
Yeah.
The last slide.
So here we find that actually, although this is a direct bandgap semiconductor, the carriers recombine through indirect band process. This is the indirect recombination. This is the main conclusion. And I'll just go to the next slide. So this is the novelty of the thesis of different chapters. Okay. Thank you.
Yeah, thank you. So are there any questions, Debu, Mishraji, Tirmal Rao?
Yeah. You have mentioned the very first slide. If the thickness goes to few atomic layers, the band gap is changed from indirect to direct band gap. What is the physical origin for that?
So here this band structure, if you see, it is a layer dependence. It has certain layer dependence. So there are, sorry, I'll just make it. What happens when you look at these different values in the conduction band? So when the layer number is changed.
What I'm asking, while you decrease the thickness, why this thing happens? What is the physical reason? What is actually happens? You just tell me the physical reason for that.
So due to change of thickness, these values, the relative energetic position changes.
Why?
So it is due to the
Why?
interlayer coupling. So when there are two layers, the interaction is different. Like this conduction band is made of px plus I pxy. Like
you have
p
already mentioned this can be easily peeled off layer by layer, na? The interaction is relatively much lesser.
Yeah.
So, yeah.
But due to this change in number of layers, there will be change in energy positions in the conduction band due to some interlayer.
It's okay. Okay. Well, and one more thing, you have mentioned that there is a correlated plasma and uncorrelated plasma. What is the frequency, plasma frequency of these two type of systems, and how do you measure them?
So while we have a correlated plasma, we'll measure. We do not directly measure it. We only know this n value. Yeah.
Okay. What is the typical? How do you know quantify the order of frequency range actually?
In
correlated plasma and
terahertz.
uncorrelated. What is the range of plasma frequency it will have?
It will come in
your
tens
system.
of in tens of terahertz.
For both.
Less than 1 MeV.
Okay. For both the systems.
No, sorry.
Which one have more frequency?
But if it is uncorrelated, it is not going to form any wave kind of thing. So we won't have a frequency there. We can only define frequency if we have the plasma, I think.
Yeah, it is just like a normal metallic kind of plasma. Is it okay? You mean to say that?
Okay. Okay, so there won't be any longitudinal wave where we can define the frequency.
Okay, so let's go to any other questions.
Yeah, just wanted to know, how does the dimensionality of the system affect your properties like absorption and band structure?
So if
you said you come from 3D to 2D.
Yeah, so in bulk, it is an indirect band gap. It has a band gap around 1.1 eV, but when you go to the monolayer limit, it has band gap of 1.9 eV. So but this direct band gap is also seen in bulk.
What is the physical origin of this? Change in dimensionality brings the change in absorption
If you
parameters.
reduce the dimensionality, there will be confinement, quantum confinement. So this band gap increases, like is this 1 upon this reduced dimension.
So in terms of condensed matter physics, it changes something. What is that change? Change in the parameter.
Could you please elaborate the question? I could not understand.
Is there a quantity in condensed matter that reflects the change in dimensionality?
Yeah.
Captures.
Screening changes a lot. That is epsilon.
DOS?
Density of state, yes.
Okay.
Okay,
right.
okay, fine. Fine.
So,
The next thing is what do you measure in transient probe absorption? What is actually your worry to do the transient probe absorption measurement?
Sorry. Here this probe is coupled to the spectrometer, and it is like integrated over some like nanoseconds of time. Although we
okay.
are
So, yeah, a quick
So my
answer.
question is, what is the measurement you perform by doing the transient probe absorption?
Oh, we find the differential absorption. So change in absorption in presence and absence of pump. So this quantity we are looking at, delta OD.
Is there anything else you can dig out from this?
Yeah, when we measure this quantity, it can tell information about whether we have a stimulated emission, we have saturable absorption or excited state absorption.
Okay.
Okay. Yeah. So one last question from Debu.
Yeah, and so you have a 50 femtosecond resolution, I think, of whatever you are set up in this transient absorption spectrometer. So can you tell me what is your coherent lifetime that you were mentioning of your correlation? You mentioned in terahertz, but I'm interested to know in time. Do you have any idea on it?
You are referring to the plasma states?
Yes, yes. Any idea on the time scale? You
So
mentioned
the
it's in
formation
terahertz.
time, yes, I missed this part. The formation time we find is around 8 picosecond here.
Okay.
If you see the rise time here around.
Okay. I'm done.
Yes, yeah, we have to conclude now. So thanks very much, Morabina.
Thank you, sir.
So
Yeah, can we get the next person, please?
Okay, sir. So our next presenter is Dr. Harpreet Kaur from IIT Ropar.
Yes, sir.
So, hi, yes, Harpreet, we can see you. Just share your slides.
And just the highlights of your work, please. Don't go chapter by chapter.
Sir, already I have actually concise the presentation.
I know,
according to the
but
time.
still, if you present too much, then we don't understand what is the real significance of your thesis. So it's your chance to say. Thank you. Go ahead.
Just maximize the screen. In full screen
Yes,
mode,
sir,
you.
yes, sir. This hello. Hello. Hello.
Hi, yes, your screen. You have to share
Hello.
the screen again.
Okay, okay, sir. Okay, if it is visible now.
Hi, yes. Go to full screen mode.
Yes, I already done. Is it visible now, sir?
Yes, yes. Please go ahead.
Okay. A very good morning to all of you. I'm Dr. Harpreet Kaur. I have recently completed my PhD under the supervision of Dr. Kailash Chandra Jena and Dr. Narinder Singh. First, I would like to thank the organizing team. First, I would like to thank the organizing team of NLS-30 for giving me an opportunity to present my thesis work, which is based on in situ probing of interfacial molecular structure of polymer and nanomaterial using some frequency generation vibration spectroscopy. So here is the outline of my presentation. First, I would like to introduce. I will discuss about the introduction and for the present research work. Then I have discussed briefly about the experimental method which we have used to predict various molecular system, which are listed here in chapter 3 to 6. And finally, I will summarize our work. Let's start with the introduction and motivation. Surfaces and interfaces exist everywhere in nature. Here you can see the examples of the natural interfaces. Here is the air-water interface, here is the air-solid interface, and this is the solid-liquid interface. So the molecular arrangement at the interface is quite unique and unique, and the property, the interfacial structure and properties at the interface quite different and unique. For example, here you can see the molecular the difference between the force experienced by the water molecule at the interface and at that one experience in the bulk is give rise to the surface tension of the liquid, and this surface tension is quite dependent on the interaction of the molecules. For example, Kian et al. Have shown that there is decrease in the surface tension when there is increase in the molecular between the nanoparticles and the surfactant. Now, in case of polymers, which are used under various environmental conditions, the interfacial structure plays a very crucial role depending upon their application. For example, in case of bioimplants, the surface coating can help to protect the implant surface from the non-specific absorption of the proteins. So our study is mainly focused on probing the interfacial molecular structure at polymer interface and also at air aqueous interface using a surface specific and chemical active tool, that is the sum frequency generation vibration spectroscopic tool. So I will briefly discuss about this SFG now. It is a second order nonlinear process in which two fundamental laser beams are overlapped at the interface, where chi2 is not zero due to non-centrosymmetric environment of the molecules at the interface. And for SFG to occur, the two fundamental laws of physics should be followed. One is energy conservation and another is phase matching condition. So depending upon this phase matching condition, one can detect the direction of this SFG beam. So the intensity of this SFG beam is enhanced resonantly when the frequency of this tunable IR match with the resonant frequency of the interfacial molecules. So the SFG spectrum is obtained as a function of frequency of tunable IR, which is upshifted in the visible region of the electromagnetic spectrum. So for the SFG spectrum, we to obtain the SFG spectrum, we have this schematic of we have this experimental setup for this, which is comprised of NDR laser, second harmonic generation unit, and this DFG unit. And also we have a detection system, which is comprised of this monochromator and PMT. So with the help of this system, we probe various molecular systems. We will discuss one by one further. And this is the actual picture of our lab setup. So now I will discuss how we have used this to probe the molecular structure and dynamics of TOS at air aqueous interface. This work is recently published in ACS Applied Nanomaterials. TOS is used as a precursor in social mechanisms to form the silica nanoparticles. And there are many parameters in the social mechanism which have to know, but our study is mainly focused on controlling the concentration parameter and also the variation of pH of the aqueous medium. So the SFG spectrum is obtained for variation concentration of TOS in aqueous medium, from which we observe that there is overall decrease in the SFG intensity with time. And also we have observed similar kind of changes at higher concentration of TOS. So from this, we actually observe that the CH moieties, and which these are the signal of the CH vibration modes, And these CH moieties get eliminated over time, which is possible due to the hydrolysis of this TOS. And further, in OH stretching region, we found that there is overall enhancement in the SFG intensity with time, and which confirm that there is hydrolysis at air-aqueous interface, due to which there is formation of negatively charged moieties, and because of that, there is ordering of the interfacial molecules at the air-aqueous interface. And further, with time, we have found this intensity enhancement is decreased, which actually possible due to the decrease in number of these or negatively charged moieties, which confirm the condensation at the air-aqueous interface, due to which this water molecules ordering is again there. And further, with time we found this decrease is continuous, so the condensation process is continue with time. And finally, there is formation of cyclic structure and nanoparticles, which lead to form of nanoparticles, which is also confirmed from our DLS measurements. So this is the very integrated intensity variation with time for this OH stretching region. We have found similar kind of trends for higher concentration as well. Further, we have studied the pH effect on the interfacial structure dynamics of TOS at air-aqueous interface, in which we have found that the elimination of the CH moiety is very faster at lower pH value as compared to that at the higher pH values, which confirm that rate of hydrolysis is very faster at lower pH values. This is also supported by the literature, from which we can see that at lower pH values, the rate of hydrolysis is faster as compared to the higher pH values. So from these studies, we concluded that the changes we have observed changes in the CH and OH stretching region of from the SFG spectrum, which confirm the hydrolysis and condensation of the TOS molecules at air-aqueous interface, which further lead to form cyclic structures and nanoparticles. And also, we have determined the impact of pH values on the hydrolysis rate of the TOS molecules at air-aqueous interface. Next, I'll discuss about the molecular and sensing molecular structure of nanomaterials and their sensing activities at the air-aqueous interface. So in nanomaterials, carbon dot is the youngest member in the family of nanoworld. This is the generalized structure of the carbon dots, and these are the main important properties and application of these carbon dots. But our studies mainly focus on the sensing applications. So in the synthesis of these carbon dots, this compound undergoes zonication process to lead to form of organic nanoparticles, and these nanoparticles further undergo hydrothermal treatment to form the carbon dots. And the fluorescence studies have shown for the for organic nanoparticles that these organic nanoparticles selectively bind with the cesium ion, whereas carbon dots for the carbon dots selectively bind with the silver ion in the aqueous medium. And from the interfacial study, we have observed the SFG spectrum for organic nanoparticles, in which we have found there is no change in the SFG spectrum, and is compared to as compared to the interfacial pristine water structure. This confirmed that this confirmed that the organic nanoparticles have no impact on the interfacial water structure, or it means organic nanoparticles prefer to stay in bulk or has a disorder conformation. Further increase in concentration of cesium ion in the organic nanoparticles fusion, we have not observed any significant change. But in case of carbon dots, we have found that there is overall enhancement in the SFG intensity in the OH stretching region, which confirm the hydrophobic ordering of the interfacial water molecules. And on addition of the silver ion to this system, we have found this overall intensity enhancement is suppressed, and which further increase have shown the appearance of CH and NH stretching modes with complete elimination of free OH at the interface. So from these studies, we have found that the organic nanoparticles, while binding with the cesium ion, prefer to stay in bulk, whereas carbon dots shows the surface coverage while binding with the silver ion. So from this study, we have found that organic nanoparticles have no impact on the interfacial water structure, whereas carbon dots have shown the ordering of the interfacial water molecules. And from the fluorescence study, we have found that organic nanoparticle preferably bind with the cesium ion, whereas carbon dot effectively selectively bind with the silver ion. And their interfacial study have shown that organic nanoparticle, while binding with cesium ion, prefers to stay in bulk, whereas carbon dots preferably binding with silver ion shows the surface coverage at air-aqueous interface. So this is about the sensing activities of the nanomaterials at air-aqueous interface. Further, I will discuss about the in situ probing of molecular orientation of a methyl functional group of polymer films with variation in molecular weight. So this is the molecular structure of PDMS, and we have found the impact of molecular weight variation on the orientation of the methyl group. So for this, first we have calculate theoretical calculation about the L factor corrections to get the real response of the medium. And these are the expression for the Fresnel factor at interface 1, which we have applied to the experimental determined SFG spectra. And this is the SFG L factor corrected SFG spectra. And the amplitude ratios of this is used to determine this ratio, and which intersects with the experiment theoretical curves which are determined from this expression, and this for various sigma values. So intersection between this experimental values with the theoretical lines give the value of the orientation at the air orientation of methyl group at the air polymer interface. So we have determined for all the polymers, and we have found that there is decrease in the orientation angle of the methyl group with increasing molecular weight, which actually confirm that free volume at the interface is actually decreasing with the increasing the molecular weight at air polymer interface. Now in the next, I will discuss about the probing the drug polymer interaction at air aqueous interface using some frequency generation vibrations for spectroscopy for two different drug systems. One is rifaximin and other is albendazole. The major problem in the drug industry is the solubility of the drugs. So for which polymers are used, which help to enhance the solubility of the drug in the aqueous medium. So first, I will discuss about the rifaximin drug, how its solubility is increased in presence of polymers, and then its interfacial characteristics which we have proved using SFG spectroscopy. This is the molecular structure of rifaximin. The solubility is enhanced in presence of these polymers. And further, the SFG studies have shown that on addition of this rifaximin drug to the aqueous system, there is overall enhancement in the interfacial in the SFG intensity in OS stretching region, which confirm that there is ordering of the interfacial molecules or interfacial water molecules of the relevant media in presence of drug. Further, we have probed the effect of polymers on the interfacial structure, from which we have found the signature, sharp signature, dominant signature in the CS stretching region, which confirm the surface coverage by these polymers at air aqueous interface of the relevant media. But on introduction to the drug to the system, in this HPMC polymer, we have found that this enhanced intensity in case of drug is actually decreased while during interaction of this polymer with the drug, and also the signature in the CH stretching region are dominating, which actually confirm that there are very prominent interactions between this drug and polymer. While the reverse case is found in case of the soluplus and PV.
Can you conclude, please? Could you conclude?
In case of second drug, if that the PVA polymer is effectively bind with this FVZ drug from SFG that aqueous interface. So I can confirm here that SFG study is very helpful in proving the interaction at the air aqueous interface during this drug polymer system. So finally, I would like to summarize my work. From the first study, I have determined the dynamics of TOS at air aqueous interface, which lead to hydrolysis and condensation, and finally formation of nanoparticles. In the second study, I have determined the sensing activities of carbon dots and organic nanoparticles. And then we have probed the orientation of methyl group at air polymer interface. Finally, we have determined the drug polymer interaction at air aqueous interface. And these are the publications and this is a conference I present. Finally, I would like to thank my supervisor, our collaborators, my lab members, DST, MHRD, and also I would like to thank IT Roper for providing the infrastructure. Thank you all for listening patiently.
Thank you. Are there any questions?
Yeah, I just wanted to know why do you go for a SFG technique rather than doing conventional techniques like FTIR or vibrational Raman spectroscopy?
Okay, FTIR, actually, the probing depth in FTIR is around 1 micrometer, which is 1,000 times more as compared to the SFG. To get the information about the interfacial molecule, we have used this SFG spectroscopy, which provide the information about the 2-3 molecular layers at the interface. So FTR basically provides the overall information about the bulk and interfacial molecules. So we can't distinguish about this system.
Okay, fine.
Yeah, Debu, any questions?
You have mentioned, you have mentioned nanoparticle formation. You confirmed from DLS. What is the size range you have observed?
Sir, it is from the 2 nanometer to 5 nanometer with increasing this.
Are these a stable one? Because you have also measured any zeta potential of these nanoparticles.
Yes, I have made zeta potential as well for this pH dependent studies. Yes, sir.
Yeah, and what is the range of that zeta potential you got?
It is variable. It is actually during dynamics. It is between minus 18 millivolts to plus 20
Is there is
millivolts around.
this CMC for this critical micelle concentration kind of thing? The polymer. What is the minimum concentration at which this can occur?
Pardon, sir. This is.
What is the minimum concentration polymer you have to load in aqueous phase so that the nanoparticle will form?
Okay, in this actually we have used just point, initially we have used higher concentration. It is on 10 volume by volume concentration, but then I have lowered the concentration to 0.1 volume by volume concentration because TO is actually immiscible in the ecosystem.
I think the question is there a physical way of expecting that at this point of time, the condition at which point of time the nanoparticle will actually form? Not what you might observe phenomenologically. Is there a physical reason?
Okay, means what is the size of the nanoparticle?
Move on to other questions, maybe. Debu, last question.
Actually, it's a very important point which Rumalai was asking. In fact, since you are using some frequency generation, SFG, it should be able to check for any phase change, right? I mean, so whenever you are breaking symmetry because of phase change, then also you should be able to detect it. So CMC should also be detectable. Did you see that happen? That's partly what I think he's also trying to get at.
Partly CMC.
Can you actually apply this to CMC? I mean, critical micellar concentration. Because you see what happens at the critical micellar concentration.
Okay.
Yeah.
Actually, in this study, I have initially fixed the concentration to 0.1, and then the changes in the system I have observed, but how much it is actually convert, we are not able to see how much it actually convert. So we have observed actually for 24 hours for every half an hour we take the new spectrum to how the changes are occurring at the interface.
Okay, so yeah, perhaps we'll conclude now. Thank you very much.
Thank you, sir. Thank you.
So can we admit the next person?
Yes, sir. So our next presenter is Dr. Rajendra Junjuri from University of Hyderabad.
Okay.
This is the last one.
Dr. Rajendra?
Yes.
Yes, this is the last one.
Okay.
Yeah.
Please continue, Rajendra.
Yeah, please keep it focused. Don't spell out the whole thesis, please.
Yeah. No, I have
Just
divided
to tell us what is it that you have done. Don't go chapter by chapter, please.
No chapters, sir. Only I have 2 chapters, like entirely thesis divided into
Wonderful,
only 2
wonderful. Thank you.
chapters.
Go ahead.
Yeah.
And don't repeat this
Yeah.
slide. We all know the topic. And
Yeah. So main motivation is this is the application of LIPS, sir. So the first application is identification of plastic waste. This is for the recycling industry, and standard detection of high energy materials. High energy materials are explosives, like remote detection of the explosives. This is for the defense application. So main motive is this, the 2 applications, and bring down the cost of the LIPS detection system, and as fast as how fast we can detect the.
Excuse me. I could not see the slides. Is the slides are displayed?
Yeah.
I'm able to see. I don't know. You have some problem in your connection?
Yeah. Now, can I start?
No, it's okay. Continue, please continue.
Yeah. So that is the main motivation. So LIPS is atomic based emission spectroscopy. It will what we can get from the LIPS data. So we can find the given element in the sample, as well as we can find the concentration of the given element. So the third important thing is the identification of the samples. So this third important property I have used application. So I have worked with the plastics as well as the explosives or organic samples. As I said earlier, LIPS is atomic based spectroscopic technique. So because of the higher intensity, the molecular information, there will be no molecular information kind, like a Raman kind of thing. Here I have shown 4 plastics. I have worked with 10 plastics. So all 4 plastics will have carbon and hydrogen. Because of the higher intensity, so molecular information will be lost. We'll get only atomic information, and all 4 samples will have same kind of elements, and we'll get the spectra look similar. So in case of LIPS for the organic samples, by looking at the spectra, it is not possible to identify which sample as which one, like NIR and Raman. So here, by looking at the spectra, it is not possible. However, this problem can be solved by using the machine learning algorithms. I have used 4 and 5 machine learning algorithm, but here I have restricted to only 2 machine learning algorithms. So if we give input data to machine learning algorithm, it can show whether they can be separated or not. So I have used a principal component analysis algorithm. It visually shows the separation among the samples or not in a reduced dimensional scale. This is the input spectra, 4 spectra I have given. So the output will be like this. Here the spectra look similar, but minute changes in the spectra can be easily visualized by using the application of PCA. So I have written code for PCA and MATLAB, and I have optimized the parameter. So PCA visually shows the separation among the samples, whether the samples can be classified or not. But quantitatively, it will not tell any. Quantitatively, it will not tell. Quantitatively, it will not show any separation. Artificial neural network is another machine learning algorithm. It quantitatively tells what is the percentage of classification each polymer or each sample. It is like a facial recognition app. First, we need to train the model. Then, after training, if you give new input, it will give the output, whether it is how much percentage it is classified. So, this is the training process. We need to stop the training process after certain time. Like I have fixed it to error to 10 power minus 4. So, I have stopped the training algorithm after 10 power minus 4. After training, it will give the output like this. Sample N is classified as 0.99%. Sample V is classified as 0.97%. This is the confusion matrix. So quantitatively, we can get the estimation rate. So in LIPS, data analysis plays an important role. I have participated in a data analysis competition, like it is conducted worldwide. They have given like so many number of samples, 138 different samples of 12 different classes. Like it is around 10 GB data. So I have applied 4 to 5 different machine learning algorithms to reduce the data size to improve the efficiency. I got around 78% efficiency. So this is published as a special publication with the conference. So this is the main application. Identification of the plastic waste. Like in the plastic waste, important thing in recycling is sorting, because if we mix 2 plastics, the final product quality will reduces, as well as it reduces the cost. One example, another example is like if you mix PET versus PVC, if you mix two plastics, HCl will be formed. That will be dangerous to the operators. So sorting is the important thing before going to recycling. So these are the current methods they will use. Resin coding like 1, 2, 4, 5, 6, 7. These are the recycling numbers. Based on the recycling numbers are zinc floating measurements used. Spectroscopically, NIR and Raman are the reported tactics. But the problem with the NIR and Raman is it cannot work with the dark colored samples or black colored samples. So it cannot overcome. But LIPS can work with dark colored samples as well as a black colored samples. So outline of the work, what I have taken, like what people have reported, like people have purchased from the company, they have worked on the original like pristine plastics, but I have taken the samples from the local recycling unit. Then I have worked with a tooth spectrometer. So the main motivation is to decrease the cost of the LIPS detection system. In LIPS, the spectrometer, the detection system cost itself is the main burden. If I go for ICCD based detector, it will be around 50 lakhs. If I go to CCD based spectrometer, it will be around 4 to 5 lakhs. Like 10 times I can reduce the cost by using the CCD spectrometer. But it will give continuum. But because of the we can use different data analysis method to tackle that problem. And I have collected the data single shot mode and 10 shot accumulation. 10 shot accumulation increases the signal to noise ratio compared to single shot. But if you want to make rapid analysis, we need to work with a single shot. So I have compared single shot how it works and 10 shot accumulation how it works. Then I have taken only 100% of the total data and I have taken only 10% of the total data. Here 10% of the data refers to I have taken part of the LIPS spectrum. So these are the samples. I have worked with 10 different samples. This first 5 corresponding to the 70% of the total plastics production. So these dots are laser irradiated area. And this is the experimental setup. This is a Maya spectrometer, low cost one. This is a Michel based ICCD spectrometer. I have collected in like ICCD 10 shot accumulation. I have collected ICCD 1 shot mode. I have collected, and with CCD only single shot. There is no accumulation or average option available with the CCD. This is the LIPS spectra. So compared to ICCD 10 shot has given best signal, like a better signal compared to this is ICCD 1 shot. So signal to noise ratio improved. In case of CCD, like continuum is observed because there is no gating to avoid the continuum. So CCD has lesser resolution, where ICCD has better resolution. It can resolve the peaks. So these are the LIPS spectra of the 10 plastics. So as I said earlier, it looks similar. Then I have employed, as I said earlier, PCA. This is a single shot, 1 shot with ICCD. This is a 10 shot. So because of the accumulation, the classification has improved. Then I performed this CCD spectrometer. I have used only single shot. So ICCD 10 shot performance is giving similar performance to CCD single shot. Like that means CCD we can reduce the cost, as well as because we are using only 1 shot identification, it will be 10 times faster. Then for the quantitative estimation, I have used artificial neural network. So CCD 1 shot is giving around 97%, which is equals to the ICCD 10 shot. Visually, we have seen from that. But the testing time, like with ICCD, 40 milliseconds is the testing time for identification one plastic. But with CCD, it is only 10 milliseconds. That means the time here, the testing time is also 4 times faster. So I have used a feature selection program. Feature selection is like thing, but like it this LIPS spectra has 22,000 2200 data points. So instead of taking all the data points, I have used random forest algorithm. It will assign importance for each data point. So this is the random forest. This A is the random forest output. So starts from 0 to 0.3. So highest variable importance means that variable is more significant. So I have kept some threshold kind of thing. Take only the data points which are greater than 0.2, 0.1, 0.05. So these are the results are like this, like 100% of the data. If I take only threshold of 0.05, the data is only 7%. Take only 7% of the data, but the accuracy is reduced by only 2%. That means if we are taking 100% of the data, I got 97%. If I take 7% of the data, I got 95%. Like drastical reduction of input data was reduced only 2%. Like then, but it reduces the testing time and training time by 4 times. So feature selection drastically reduces the training time and testing time. So here the outcome is CCD one shot identification is close to ICCD 10 shots, and analysis time can be reduced by 10 times feature selection. So these are the 4 publications, and it is this work has appeared in OSA Optics Year Review 2020. The second application is like identification of explosives. So initially I have worked with 1 meter using ICCD based spectrometer. Then I have extended the standoff distance to 6.5 meters using a low cost based spectrometer. This first experiment served as a initial step towards the working of the standoff detection. So this is the schematic of the standoff detection. I have used only single lens focused to 1 meter, and again I have used one more lens to collect the from 1 meter distance. So this is this 1 meter lens again, one more lens is used to collect optical emission. This is spectra collected at 1 meter. So these are the using classification using PCA. It worked well, but in real time the standoff distance is unknown, so we need to work with double lens system. This is the typical experimental setup I have used in the double lens system. This is the first lens, this is the second lens. So here is the target. The distance is around 6.5 meters here. Then plasma formed. This plasma is collected with the telescope. Then later I have used a small telescope instead of using this big telescope. It collected to this region. So this is the experimental setup. Then optimization of the focusing system. In real time, if you want to make a system, it should be compact in size and weight. So I have chosen 2 lens systems. So this is the second lens system has given lesser spot size. Lesser spot size means with more intensity. Hello. Yeah. Okay.
You'll have to conclude quickly now, please.
Yeah. So it has optimization of collection system has also improved the result. Then these are the identification of explosives and explosives. So the red one is explosives and black one is non-explosives. So we can able to show the separation among the explosives and non-explosives clearly. Then identification as using ANN. So greater than 94% it is given, and within the explosives also it has shown good separation. Also I got around more than 95% separation for the within the explosives also. These are the chapter. I have 2 publications for this chapter, and these are the conclusions. Yeah.
Okay.
These are my publications. Thank you.
Okay. Yeah. Thank you so much. Are there any questions?
Yeah, I have some questions. Yeah, few questions.
Yeah.
Please.
Yeah. So you have mentioned the plastics. You have given a training algorithm, PCA. But how many types of plastics you have chosen?
Yeah, 10 plastics I have to choose.
Okay, you did PCA, but you have trained. What is each plastic? How much data you have trained?
Yeah, each plastics I have taken 200 spectra, total 2000 spectra.
Okay, fine. So then without actually, have you tried any SVM, support vector machine? Have you tried?
Yes, sir. I have tried, but I have not put it in the results, because.
No, okay. What is the accuracy of this? Suppose if I put 10 more plastics.
Okay.
Okay.
So
if I put additional 10 more, whether your prediction algorithm still work there, or you need to do something else?
No, sir. We need to train the sample.
No, you have trained. See, my question is, you have did PC1, PC2, or PC3 also?
Up to PC3 I have taken.
Okay. So if you add, suppose I have 100 plastics I have given, can PC1, PC2, PC3 can able to classify?
No, sir. If it yes, yeah. It can able to show the difference, but quantitatively if you show it belongs to which one, it is not possible. It will tell like if you train with the 10 plastics, if you give 11th one unknown, it will say it belongs to which one. So training is training library is important, sir. If you want to test the new one.
Okay.
Okay.
Yeah. Any other questions, please?
See, as compared to
Yeah, I think the
other
question was,
techniques, how this LIPS is superior for explosive detection?
Sir, Raman based, like if you want to stand off, Raman based will give molecular fingerprint, but at remote mode it will give lesser intensity. So in that way it will be good, sir.
So whether the sensitivity wise, whether this is better or Raman is better?
Sir, sensitivity wise, like if it is a trained library, it is better, sir. LIPS is better.
No, what is the detection limit of SCRS and LIPS?
Okay, quantitatively, sir, quantitatively, LIPS, like CERS is like, it is on the ppm, LIPS is not that much sensitive, sir.
Okay. So any question, Debu?
yeah, so the ppm level part was the one which I was going to ask, but anyway, that's asked. There's one other quick question, which is that your training and your results, the classification, did you find any mathematical relationship? So for example, basically as the sample size increases, typically we know things go as root over N, right? So that's why
Yes,
we
sir, yes.
increase the sample size to get a better understanding. In your
Yes, sir.
particular case, is there any mathematical statement that you have managed to make because of your study?
Like based on the sample size, sir, like you're asking, like.
I mean, yes. So basically, you said that you had taken 100 samples of each or like 200 samples of each and 10 classified classification criteria.
So,
Had I
yes, sir.
taken 1,000 samples, did I do a better job or worse job? Or if I went
Yes,
to
sir.
100
Yes,
samples?
yes. Yeah. More training data, the results will be more accurate, sir, actually.
No.
You're correct.
That's just a. This is not a quantitative statement. Have you managed to come up with a quantitative statement? That's the question.
Mathematically, no, sir. I have like tried to change different parameters to work with that. Like minimum 30 samples. Like I got
So I
30
believe he has
samples.
not done that yet.
Yeah.
Fine. Yeah. Fine.
Okay. So
Okay.
thank you very much.
Okay, sir.
And you can disconnect. And I want to tell the judges that there is another meeting at 12 o'clock for which you may have got a Zoom link.
Yes.
Yeah.
We'll be sitting with Dr. Alak Ray, I think.
Okay. So, sir,
we come back in about 15 minutes.
Okay, sir. So
is it the same link?
Session by.
No, I think it's a different link.
Yes, sir. A link has been generated and shared to all the judges in their email IDs. So, so you may join those meetings for reviewing the thesis.
All right. Yeah.
So thank you all our esteemed judges for evaluating 7 theses in this session, and thank you all the participants for presenting their work in this NLS-30. Thank you.
Thank you. So we'll meet again.
So do join in that link as soon as possible.